Now I shall discuss some terminologies used in the thermodynamics or in the introduction to thermodynamics. The, the one term which is used in the thermodynamics is a spontaneous process and the non-spontaneous process, the term used. Spontaneous process is will proceed automatically. There is no need of giving any external agencies or need of any external energy. There is no need of activation energy. So, or it may require a small activation energy just to start the process. And once it starts, the rest will proceed without the need of an external energy source. The good example is the combustion, the burning of a substance to produce a heat and energy. You may have a light the substance first, but once the substance is burning, it continues. Like water flow. The water flows downhill spontaneously. We cannot reverse the direction of flow of water with some external aid, or the diffusion of solute from a more concentrated solution to a less concentrated solution. When these are brought into a contact, proceeds spontaneously till the concentration becomes uniformly or the same till the equilibrium is attained. But this process cannot be reversed because once the concentration becomes uniform, it is not possible to make spontaneously one part of the solution more concentrated than any other part. Then even electricity flow spontaneously from a point of higher potential to a point of lower potential. The direction of flow of current can be reversed only by applying the external field in the opposite direction. That is a non-spontaneous process. And even okay, these are the few examples for a spontaneous process. And if the reaction, that process that take place with the help of an external energy, activation energy, then that process is called a non-spontaneous process. A good example is the photosynthesis, a process in which a plant used to make a glucose. A photosynthesis requires energy, and that energy is derived or taken by the sunlight to drive a chemical reaction. And this reaction takes place only at daytime, not at night. And this is a non-spontaneous process. Okay, spontaneous and non-spontaneous process. So this is a good example for spontaneous and a non-spontaneous process. When a monkey sees banana, spontaneously it try to take. So this is a spontaneous process. Okay? Then the next term is a enthalpy. Or you can spontaneous enthalpy. Enthalpy usually expressed in terms of H, the heat change enthalpy. Enthalpy is a property of thermodynamic system defined as the sum of the system's internal energy and the product of its pressure and its volume. If the reaction takes place, that time usually either the heat energy is evolved or the heat energy is absorbed. So we usually consider the system and surrounding. So heat energy may be absorbed by from the surrounding to the system, or the system may give heat energy to the surrounding. Based on this, we can consider like exothermic reaction and endothermic reaction. In case of endothermic reactions, it usually absorbs heat energy from the surrounding. Whereas in the case of exothermic reaction, so system gives out heat energy to the surrounding. This enthalpy, the change in heat energy, usually expressed like it depends on internal energy of the system and the product of its pressure and volume. So it expresses H is equal to U plus PV. Or we may express like delta H is equal to here delta H is equal to delta U plus P delta V, where delta H is equal to is considered as H2 minus H1, the initial and the final variation in the enthalpy. Okay, that is the a small change in enthalpy. Usually we express in terms of delta H. So usually, if heat energy is absorbed from the surrounding to the system, then enthalpy increases. If heat is given to the surrounding, then enthalpy decreases. Based on that, we will consider endothermic and exothermic reaction. If delta H is positive, then that is, if enthalpy of a reaction is a positive, then the reaction is considered as endothermic. If the reaction is endothermic, means delta H is positive. If delta H is negative, then the reaction is exothermic. That means heat is given to the surrounding. Okay, there are two exothermic and endothermic reaction. If delta H is a positive, then the reaction is endothermic. If delta H is negative, then the reaction is exothermic. So we can express like this. Here a chemical system, to that if you add one reactor to one reactant, if you add another reactant, the reaction, during the reaction, the heat may be absorbed from the surrounding or it may give to the surrounding. See, if heat energy during the chemical reaction, if heat energy is given to the system, then that reaction is considered as exothermic reaction. So delta H is negative. In case of endothermic reaction, here the heat energy moving to the from the surrounding to the system. So delta H is positive. Okay. The next term here, enthalpy delta H is equal to delta U plus delta V. Then internal energy, here what we considered here is enthalpy is related to delta U or U, internal energy. Then what is internal energy? It is the sum of the kinetic energy and the potential energy in the substance. Okay, a sum of kinetic energy and the potential energy of the substance is called as a internal energy. Internal energy is defined as the energy associated with the random or a disorder motion of the molecules. There may be an order motions if the particles are bound together with a good bonds, then highest internal energy is observed. The internal energy, also called as a thermal energy, is the energy of an object or a substance due to kinetic and potential energy. Okay, associated with the random motions, and it is energy usually expressed in terms of kilojoule or joule. And the next one is entropy. The term what we observed is a entropy. It is a measure of randomness. The entropy is the measure of randomness of energy in a system. A measurement of degree of randomness of energy in a system is called entropy, and it is expressed as S, entropy. The change in entropy is delta S, expressed as delta S, that is S2 minus S1. Okay, that is what we called it as a change in entropy. And the lower the entropy, the more order or less random is observed. That means as the randomness entropy decreases, the system is more considered as a more ordered arrangements. The order arranged system is observed. And here for the entropy of a irreversible system, we can express the change in entropy is delta S equal to Q by T, reversible reaction. The quantity, the Q by, it is usually expressed in terms of Q by the change in entropy for a finite change of state of a system at constant temperature is given by delta S is equal to Q by T reversible. It is a state function and it is an extensive property depend upon the amount of substance involved. Here the amount of heat absorbed reversibly by the system from the surrounding at a temperature T. Q is a quantity of heat absorbed from the system to the surrounding at a temperature T. It usually measures the randomness of the system, measure the unavailable, or in other words, it measures the unavailable energy. For a spontaneous process, entropy is always positive. Say like spontaneous process may be a melting or dissolution, melting of ice. Here, order state to it moves to disorder state. Ice are ordered arrangements. From order state to when it moves to a disorder state, the randomness increases. If the water freeze and forming ice, then again here what we observe, the ordered arrangement is observed, the entropy decreases. Okay, from in all spontaneous process the entropy is positive. The next term is a free energy. It is free energy is a the energy. It is defined as the maximum amount of energy available to a system to perform useful work. Here, the sum work is nothing but the sum of total of entropy change of a system and the surrounding, which serves as a criterion for a spontaneity or feasibility of a process. Mainly, this free energy change, it tells about the feasibility of the process, or the entropy that tells about the feasibility of the process. If the total entropy change is a positive, then the process is feasible. If it is zero, the system remains in a state of equilibrium. The system remains in the state of equilibrium. If the process is feasible, then entropy should be positive. If it is zero, the system remains in the state of equilibrium. However, in order to decide about the feasibility of a process, we shall have to know the entropy change of the system as well as that of the surroundings. This is not always convenient. Entropy change in terms of other state function also be determined. Like the other state function, what we observed is a free energy. It is defined as the maximum amount of energy available to a system to perform a useful work. So it is usually expressed based on a Gibbs-Helmholtz equation, that is delta G is equal to delta H minus T delta S. See, delta G is considered as a Gibbs free energy change, delta H is an enthalpy change, T is a temperature, and S is the energy which is lost in disordering the system. That is what we call it as an entropy change, or Gibbs free energy change, which is equal to total energy change for a system minus energy lost in disordering the system. If the reaction is exothermic, then delta H is negative. The entropy increases or delta S is positive. So based on that, for a spontaneous process, delta G is negative. Delta G is negative means the reaction is spontaneous. If the reaction is a spontaneous, we observe delta G negative. Delta G, if you get a positive, means the reaction is non-spontaneous. Okay, but the reaction is spontaneous at all temperature. In most of the reaction, what we observed is a spontaneous reaction. In that, free energy change of a reaction is negative. For all spontaneous process, free energy change is negative. Now, coming to the first law of thermodynamics, is a law of, it is also called as a law of conservation of energy. The first law of thermodynamics is also called as a law of conservation of energy. State that the energy can neither be created nor be destroyed. Energy can only be transferred from or changed from one form to another. So this law, what we called it as a law of conservation of energy. Energy can neither be created nor be destroyed. Energy can only be transferred or changed from one form of energy to another form. Example, turning on a light would seems to produce energy. However, it is an electrical energy that is covered. So the first law of thermodynamics, we relate into the equation, that is delta U, that is change in internal energy, equal to heat absorbed to the system minus work done by the system. The change in internal energy of the system is equal to heat added to the system minus the work done by the system. So it is in this way mathematically we can express the first law of thermodynamics. So we can observe from the picture, light energy is converted into chemical energy, or chemical energy can be converted into electrical. During this conversion, there may be a little loss of energy, but it is not possible to create or completely destroy the energy. We can convert one form of energy to another form of energy. That is first law of thermodynamics. Then coming to the second law of thermodynamics. The second law of thermodynamics says that entropy of an isolated system always increases. So the entropy of an isolated system, it's always increases. In simple way, the entropy of the universe always increases and never decreases during the course of any spontaneous reaction. If you consider any spontaneous reaction, the entropy of the system increases. It will not decrease, or it will not remains the same. It will, entropy of the system decreases. In case of non-spontaneous, we are not considered. In the second law is mainly considered the spontaneous process. The second law of thermodynamics says entropy of an isolated system always increases, or the entropy of the universe is nothing but an isolated system. It increases and never decreases during the course of any spontaneous process. Isolated systems spontaneously evolve towards thermal equilibrium. Isolated system means it always it move towards the equilibrium, that is heat flow from a high temperature to the lower temperature. It is a spontaneous process, that is it reaches the equilibrium and the state of maximum entropy of the system is observed. Or even the block of ice, so it melts, so entropy increases. Okay, this law helps to predict the spontaneity and the feasibility of the process, that I already discussed during entropy of the reaction or entropy. The second law of thermodynamics whether the tells whether the reaction is a spontaneous, or we can predict whether the reaction is a spontaneous or non-spontaneous process. Okay. Today we shall discuss about the introduction part of electrochemistry. Okay, what is electrochemistry? What do you mean by an electrochemical cell? All those things we shall study in this module. The first of all, I'll take what is electrochemistry. Okay, the electrochemistry you've already studied. Think it is a branch of chemistry that deals with the properties and behavior of electrolytes in a solution and the interconversion of chemical energies into electrical energy. It's a branch of chemistry, or in other words, also it is expressed that it's the branch of science. Okay, the mainly deals with the interconversion from chemical energy to electrical energy. Okay, mainly deals with interconversion from chemical energy to electrical energy. Okay, see. That the chemical energy may be changed into electrical energy, or electrical energy may change into chemical energy. Entire things that deals with the electrochemistry. See, then to develop to convert a chemical energy into electrical energy, we need a cell or a device, and that device, what we called it as a electrochemical cell. Okay, an electrochemical cell is a device which can able to convert chemical energy into electrical energy, or vice versa, or electrical energy into chemical energy. Okay, so it is a arrangement of two electrodes. Okay, it's an arrangement. Later I'll tell you what is electrode. Okay, an electrochemical cell is a device which can able to convert chemical energy into electrical energy, or electrical energy into chemical energy. Based on the reaction that taking place in the cell, it is again classified into two categories. The one, what we call it as a galvanic cell, it mainly converts chemical energy into electrical energy. Okay, it converts chemical energy to electrical energy. Okay, called it as galvanic cell. If the reaction is reversed, that is, if electrical energy is stored in the form of chemical, then it is called as electrolytic cell. Okay, so collectively the device what we call is a electrochemical cell. So that electrochemical cell is defined as a single arrangement of two electrodes in one or more two electrode or one or two electrolytes, which converts chemical energy into electrical energy, or it may convert electrical energy to chemical energy. See, the this is an arrangement. This is a good example for electrochemical cell, particularly a Daniell cell, or it is an example for galvanic cell. Example for galvanic cell. It is an example for galvanic cell. Okay, which converts electrical energy into chemical energy. Okay, or it is simply called it as a Daniell cell. As you already know, electrochemical cell is a device or a single arrangement of what I written, two electrodes in one or two electrolytes, which converts chemical energy into electrical energy. See, here both I explained. Here one type of electrolyte is used, whereas here the two different electrolytes are used. Okay, it is consists of a single electrode arrangements. Okay, here also the another electrode. These two electrodes are clubbed. Okay, these two electrodes are clubbed by means of a salt bridge. This is what we call it as a salt bridge. Okay, say that cell, the entire thing, what we called it as a electrochemical cell. Okay, electrochemical cell usually made up of two electrodes. Okay, they are connected by means of a salt bridge, or here you may observe a single two electrodes which is present in the same electrolyte solution. Okay, so that's what we called it as electrochemical cell, particularly galvanic cell. You already had it. There are two types of electrochemical cell, galvanic cell and electrolytic cell. Now, the galvanic cell is an electrochemical cell. It produces electricity as a result of spontaneous reaction. What is that spontaneous reaction you observed? The spontaneous reaction observed is a redox reaction. The reaction that taking place is a redox reaction. Okay? At anode, oxidation takes place, and the cathode, reduction takes place. At cathode, reduction takes place. Here, it may usually take place due to the spontaneous redox reaction. Here, I just written the spontaneous reaction. What type of reaction it is? Yes, it is a redox reaction. I think you already know redox reaction means. That is, what do you mean by redox reaction? Anyone? Just unmute and answer it. What do you mean by redox reaction? What do you mean by redox reaction? Oh no.
Both oxidation and reduction reactions.
The reaction in one cell, or sorry, one electrode, oxidation takes place, in another electrode, reduction takes place, and this reaction that taking place simultaneously. Okay, that is a spontaneous reaction take place. Okay, that's a reaction what we called it as a redox reaction, and that type of reaction is observed in a galvanic cell. The galvanic cell, generally, I already discussed, it generally consists of two electrodes dipped in a two electrolyte solution, which are either it is separated by means of a porous diaphragm or connected by means of a salt bridge. Okay, so this galvanic cell, it consists of two electrodes Okay, that is a metal is dipped in a electrolyte solution of its own ions. Okay, two electrodes, and these two electrodes either it may be connected by means of a salt bridge or just a porous diaphragm that separates the two electrodes. And that cell, what we called it as a galvanic cell. And you studied a well-known cell, that is Daniel cell. I think in the PU you already studied the construction working of Daniel cell. The Daniel cell consists of two electrodes. The one electrode, what we observed, is a zinc electrode. Okay, the one electrode is a zinc, another one is a copper electrode. These two electrodes are coupled by means of a salt bridge. Here, the one zinc electrode, how we construct this zinc electrode? It's a simple way. A zinc metal is dipped in a zinc sulfate solution. Okay, so here plenty amount of what the ion present in the solution, that is Zn2 plus ions. Okay, zinc metal dipped in a zinc electrolyte solution. Okay, and this one, what we call this entire thing, what we call it as a single electrode, called it as single electrode. Clear? See, a metal is dipped in a solution of its own ion. Same way, the other electrode, the copper, is dipped in a cupric sulfate solution. Okay, and these two electrodes are connected by means of a salt bridge. Usually, we connected by means of a salt bridge. So that the one electrode act as a anode. How the current generated? That is by passing an electron, okay, from one electrode to another electrode. See here, one electrode act as anode, the other electrode act as cathode. Here, this electrode zinc act as anode and copper act as cathode. Okay. But if you observe the charge carried by the zinc electrode, it is, what is the charge carried by the zinc electrode? Anyone? What is the charge carried by? If you observe the picture diagram, so then you can predict easily.
Negative.
Positive.
Huh? Negative or positive? One answer I got positive, another answer I got negative. Which one is the correct?
Positive.
No. See, generally electrolytic cell anode is positive. But here the current is generated, that is using electrode. Electrode means it's not just a metal, it is a metal which is dipped in a solution containing its own ion. This entire thing, what we call it as electrode. Okay. In electrolytic cell, just a copper metal if you take, it is electrode. Yeah. That time you can take the anode is a positive electrode. But here it is a negative electrode, not positive. Whereas cathode is a, I'll tell you why it takes a negative charge. Okay. Cathode is a positive electrode. When these two electrode is connected, there is a, these metals are connected by means of a wire to voltmeter. So an electrical energy is generated. Now the question comes. So why the zinc takes placed at anode side and the copper is placed at cathode side? What is the reason? Anyone? Is it possible to answer? Here, instead of putting the copper here, if I put a zinc metal dipped in a zinc sulfate solution and the copper dipped in a copper sulfate in a reverse order, if I place, is it possible to generate a current? Is it possible to convert chemical energy into electrical energy? Just think, these things you already studied. Why? The zinc metal is anode. In the Daniel, particularly, I'll take a Daniel cell. In Daniel cell, zinc, okay, this is zinc electrode act as anode. Whereas copper cathode. What is the reason? Do you heard this one? These things you heard? Heard it? Huh? I written single electrode potential. Studied? Anyone unmute yourself and answer Shodhan? No? Yeah. Answer it. Try to answer. It may be right or wrong. Ankit? Hmm? Prasanna? Why? Why we take zinc electrode as anode, copper as cathode? This all depends upon the single electrode potential. Yen maligi bitra? Huh? Answer it. This is studied. You know some of this. Yeah, electrochemical series. You heard the word electrochemical series? Huh? Studied it or not? Electrochemical series. Anyone, please unmute yourself or put it in the chat box. No problem. Hmm? Yeah, electrochemical series. Electrochemistry. Studied?
Yes, ma'am.
You studied, is it? So, any concept under electrochemical series, do you remember? It may be right or wrong. If it is possible to recollect, please recollect and answer. Under electrochemical series. Yes, anyone? It's a arrangement of increasing or the arrangement of electrode potential. Okay, electrode potential of almost all the electrode with the increasing order of their reduction potential. Okay, their reduction potential. If you observe the electrochemical series, you can observe in the first thing is lithium, like this, Li bar Li, and Mn2 plus bar Mn. Huh? Here they written some number, minus 3 point. I am not remember 3 point something, like, and somewhere mid you may observe H plus bar H, that is 0. Then you may observe Cu2 plus bar Cu, that is plus 0.34. Yeah, here somewhere you may observe Zn2 plus bar Zn minus 0.6. Okay, see here zinc electrode, that is minus 0.76, whereas copper electrode is 0.34. Yeah, so this is the copper electrode reduction potential and this one is the zinc electrode potential. Here among the two, the one electrode potential is higher compared to other. Which one is higher? The copper or zinc? I already written zinc electrode potential minus 0.76. Copper electrode potential is 0.34. So which one is the positive one among the two? Here we use zinc and copper. How this electrode potential generated? When you dip zinc metal is dipped in a zinc sulfate solution. Copper metal is dipped in a cupric sulfate solution. Okay. That time the zinc developed a potential of about minus 0.76. Whereas here we observe 0.34. Okay. Among the two, which one is highest? Higher? Here copper. Is it? 0.34 potential. So if you choose a two electrode X, I'll take one electrode X, another electrode Y. Okay. Based on their standard reduction potential, based on their RP, that is reduction potential value, we choose anode and cathode. The one which possesses a higher electrode potential is taken as cathode. Okay. Higher electrode potential is cathode. Is it clear? Always you have to solve a few problems based on this. Okay, then you have to choose which electrode act as cathode and which one act as anode, which one are reduction electrode and the one is a oxidation electrode. So here the copper is a higher electrode potential, so it is taken as a reduction electrode, and reduction electrode is always, if this is a sign convention, always placed to right side of the cell, and the oxidation electrode always placed at left side of the cell. Here, this is about the Daniell cell. Then, what type of reaction you observed in this cell? Okay, the Daniell cell, you already know, it consists of zinc electrode and the copper electrode. Okay, and also you know the zinc electrode is an anode and the copper electrode is a cathode. Why zinc acts as anode? Because here oxidation reaction take place. Okay, always the oxidation, if the reaction is oxidation, then that electrode is considered as an anode. Okay, say zinc gives two electrons. You may observe Zn gives two electron forming Zn2 plus. Okay, oxidation reaction take place at the same time. The simultaneously that electron is consumed by cupric ion forming copper. So the net cell reaction is zinc interact with the cupric ion forming or gives Zn2 plus Cu. Okay, this is a net reaction what we observed in a Daniell cell. Okay, now I already discussed about the positive and the negative charge carried by the electrode. Why the electrode, this one, zinc electrode is anode and it carries negative charge, and the copper electrode carries a positive charge. I already discussed. Now I tell why this one. Here, if you observe the pressure which exists in this electrode, here, how we construct this electrode? Zinc metal is dipped in a zinc sulfate solution. Cathode reaction. At anode, what type of reaction that take place? You know, the anode reaction is a oxidation reaction. Why it is called as anode? Because it undergo oxidation. If a reaction that taking place in a cell is an oxidation reaction, then that electrode called it as anode. Same way, if the reaction that taking place in a cell called is a reduction reaction, then that is called it as a cathode. Okay. See, in the Daniell cell, what you observe, zinc electrode dipped in a zinc sulfate solution. Okay. So their electrode potential is minus 0.76. So that's why it is taken as a anode electrode. And the copper electrode is a 0.34 electrode potential volt. So that's why it is taken as a cathode. The anode means zinc ion or zinc moving to the solution and forming Zn2 plus 2 electron. This type of reaction take place. Here, a plenty amount of Cu2 plus ion exists in the solution. When you apply or when you connect these two metal, that time, so as a zinc ion moving to the solution, this electron to an external circuit and it come in contact with the Cu2 plus ion. So the cathode reaction becomes Cu2 plus ion takes two electron forming metal copper, okay, and they get deposited. So this is the actual anode cathode reaction that observed in the Daniell cell. Okay, so the net reaction is the sum of the two reaction, anode reaction and cathode reaction. Now coming to why I took the anode is a negative electrode. I am discussing this one. Is it? Anode is a negative electrode and cathode is a positive electrode. Usually the anode in all electrolytic cell, we take anode is a positive electrode. Is it? Yes or no? Anode means generally we consider it is a positive. Is it?
Yes, yes.
Yes, ma'am.
But in the case of electrochemical cell, it is not it is the charge carried by the anode electrode is not positive. It is negative. Okay. Why it becomes a negative? Now I'll take this one. Why that anode is a negative electrode? Okay. See, you know the reaction that taking place in the electrode here, that is Zn giving rise to Zn2 plus 2 electron. This is a reaction that is observed in the electrode. Okay, that means a zinc metal, here a zinc metal, okay, here I symbolize this one. Zinc metal undergo oxidation and Zn2 plus ion is moved into the solution, or this plus charge is loaded in the interface of the liquid and the solid junction. Yeah, clear? So all positive ions, Zn2 plus ion, moving from metal Zn to a solution. What leaves? What are the things here now? The net reaction is this one. All Zn is moved to solution. The remaining things is, what is the remaining thing? That is electron. That is symbolized like minus sign. Yeah. So the metal now takes, what is the charge? Metal becomes negative. Is it? Is it? Yes or no? Hmm?
Yes, ma'am.
Metal charge is negative. Yeah, that's why the anode is represented as a, or taken as a negative electrode. Is it clear? Because of this reaction, Zn, in case of electrolytic cell, we simply, it's not involved in the electrolyte solution. In electrolytic cell, a metal or the reaction, what we written, we write same thing, yeah, Zn giving rise to Zn2 plus 2 electron, but in that it is not dipped in a electrolyte solution of same ion, okay, in case of other electrode, I mean cell. But in the case of electrochemical cell or like Daniel cell, a zinc electrode is dipped in a zinc sulfate solution. So due to difference in the pressure, that is osmotic pressure, so you heard this word, is it? Osmotic pressure. That is a pressure which exerted in the solution, okay? And due to the less osmotic pressure, in case of zinc electrode, zinc ion move into the solution, leaving behind equal number of electron on the metal surface. As a result, that metal takes negative charge. Or in other words, in Daniel cell, anode takes negative charge. Okay, so this movement of ion, okay, to the solution or from solution to the metal, that depends upon the pressure exerted on the metal or and the solution. You already know the solution. In the solution, we observe osmotic pressure, whereas in the metal, the pressure exerted in the metal called it as solution pressure. Okay? Called it as solution pressure. If the osmotic pressure is, or if the solution pressure is more than the osmotic pressure, then the metal ion move into the solution, leaving behind equal number of electrons. Okay? Or in some cases, osmotic pressure is less than the solution pressure. Sorry, osmotic pressure is more than the solution pressure. That time, usually high pressure side to low, movement is high pressure side to low pressure. Here this osmotic pressure is high compared to the solution pressure. As a result, when you connect, as a result, Cu2 plus ion, they migrate towards the metal. Okay, ion entering into the copper metal, leaving behind a negative SO4 2 minus. Clear? That is Cu2 plus, they try to take electron and get deposited as a metal copper. Okay, so these Cu2 plus ion which present in the solution, they migrate towards the metal. Okay, and that means this metal, the thing is loaded with the positive charge. So as a result, the cathode becomes a positive charge, and this cathode is surrounded by a positively charged Cu2 plus ion is surrounded by a negative SO4 2 minus ion. Clear? So here the cathode we consider taken as a positive charge. Why? Because the osmotic pressure is more than the solution pressure. More Cu2 plus ion move into the solution. Okay, it move into the solution. As a result, the metal takes a positive charge. The entire electrode becomes a positive charge. Okay, and how the electrode potential is generated? You know, in the case of anode, Zn move into the solution as Zn2 plus, leaving behind equal number of negative charge. So this negatively charged metal attracts a positive ion which present in the solution. Okay, as a result, there is a development of what we call it as electrical double layer. Okay, development of electrical double layer that gives the, that is again the due to change in the charge or the potential, an electrical double layer is developed and that develops the potential, called it as single electrode potential. Here this potential is generated due to this reaction, and this reaction is a oxidation reaction. So that's why this potential called it as oxidation potential. Okay, the potential developed in the zinc electrode we considered as a oxidation potential, but always the potential should be expressed in terms of reduction tendency, not in terms of oxidation tendency. Even though here the electrode undergo oxidation reaction, okay, if you observe the oxidation potential of this electrode, it is 0.76. It is 0.76. But while calculating or while expressing the electrode potential of zinc, you have to express in terms of reduction tendency. Okay, reduction electrode potential. So the same magnitude with opposite sign. It becomes same magnitude but opposite sign. So oxidation potential is 0.76, so that the reduction potential becomes minus 0.76. Okay, here in the case of cathode copper, Cu2 plus takes 2 electron and get deposited as a metal copper. Cu2 plus ion move into the solution. So as a result, metal takes positive charge, and this positively charged components or the metal attracts negative ion which present in the solution. Again here development of electrical double layer, or it generates a potential. Okay, and this potential, what we call it as a reduction potential, that takes place due to the reduction reaction. This concept, I think it is clear. Yeah, reduction reaction. Okay, so there are two types: oxidation reaction and reduction reaction. If you connect these two electrodes and the internal connection is done by means of a salt bridge, there is a formation of electrochemical cell. Yeah, formation of electrochemical cell. One electrode reduction reaction take place, another electrode oxidation reaction take place, and this reduction potential of this electrode is 0.34. If you want to express the oxidation potential, how much it becomes? Copper oxidation potential. Anyone? Copper oxidation potential. Yes, unmute yourself. You know the zinc oxidation potential is 0.7. Yes, yes. Yeah. No, I asked.
0.34.
Huh? See, I want here is a reduction potential. This is not oxidation potential. I want oxidation potential of the same electrode. How much it becomes? Oxidation potential of this electrode, copper electrode.
Minus 0.3.
Yes, minus 0.34. It becomes minus 0.34. But always we express the electrode potential in terms of reduction electrode. Okay. See, this is about the origin of electrodes. Now, I'll take how we represent the galvanic cell and how we represent the electrodes. Okay, galvanic cell picture, you know, this is a galvanic cell. Okay, you know very well here, galvanic cell. Representation of this galvanic cell. See, here zinc metal is dipped in a zinc sulfate solution. What is the reaction you observed at anode? Anode reaction you already studied. Zn giving rise to Zn2 plus 2 electron. Okay, the cathode reaction is Cu2 plus 2 electron giving rise to Cu. Yeah, then the anode electrode is represented this way. Here Zn is involved. Zinc metal dissolved into the solution as Zn2 plus. So we represent this way. See, Zn, okay, is dissolved in the form of Zn2 plus. Is there same phase? this one and this one, Zn and ZnSO4, there's a difference in the phase. The one is a solid, another one is a liquid, and that difference is indicated by a vertical line. Okay, sorry, by a single weight represented by a single, it is represented by a single vertical line. Okay, by a single vertical line, I'll represent here. Bar Zn2 plus. Clear? This is a anode electrode or oxidation representation of oxidation electrode. Similarly, the reduction electrode, if you want to represent here, Cu2 plus ion. What is the reaction you observed? Cu2 plus ion takes electron and forming Cu. The active component is Cu2 plus and that deposited as a Cu. Okay, they are different by means of a phase. Okay, a vertical line. Okay, we are represented by a vertical line. So, in general, we can represent the anode representation is Zn bar Zn2 plus. Clear? Zinc move into the solution as Zn2 plus. Reaction is Zn gives or Zn2 plus 2 moles of electron. Clear? So, we represent Zn bar Zn2 plus. Similarly, the cathode reaction Cu2 plus 2 electron get deposited as metal copper. So we can represent Cu2 plus bar Cu. Okay. So this is anode representation and this one is a cathode representation. Or you may represent instead of writing Cu2 plus, you may represent a complete solution CuSO4. Okay. Like I represented here CuSO4 bar Cu, or you may just represent Cu2 plus bar Cu. Then the sum of the two representation we consider it as a cell representation, and the anode represent, you have to write anode representation first. So then cathode representation Cu2 plus bar Cu. And these two electrodes, okay, these two electrode, how we connect? How we connect these two electrode? By means of a salt bridge, and that is represented by means of a double vertical line. This is a cell representation. I think now it is clear. Electrode representation and the cell representation. And while representing a cell, always the anode representation, you have to write it in the left side and the cathode representation right side. Or in other words, the oxidation electrode, you have to write it in the left side, and the reduction electrode, you have to write it in a right side. Or the negative anode, negative electrode here, positive electrode right side. Clear? So this is about the representation of the galvanic cell. Okay. And you already studied there is a potential, the difference in the potential between the two electrode. At one electrode we observe minus 0.76, in particularly denim, and the electrode is a 0.34. Okay, and this difference in the electrode potential in turn shows the EMF of the cell. Okay, so we can represent EMF of the cell equal to E right electrode, or I can take E naught right minus E naught left. That is the electrode potential of the right electrode minus the electrode potential of the left electrode. Okay. That is, we normally represent the EMF or electromotive force. What do you mean by EMF? That is, okay, that is the difference between, or the difference of potential which causes of current to flow from an electrode of higher electrode potential to an electrode of lower electrode potential. That's why we write E cathode minus E anode, that is nothing but E cell. In case of zinc electrode, the electrode potential of zinc electrode Zn2 plus bar Zn is equal to minus 0.76. While writing, I wrote Zn2 plus bar Zn. What is the reaction? Zn2 plus 2 electron giving rise to Zn. That means I wrote reduction potential or reduction reaction or a reduction potential. Then cathode electrode is Cu2 plus bar Cu, that is 0.34 volt. Okay, that is 0.34 volt. So how we write the reaction? Cu2 plus 2 electron giving rise to Cu. Okay, now we can able to calculate the EMF of this cell. EMF of this cell is equal to, you already know, E cathode minus E anode. Yeah. What is the quantity? Both we represent the reduction potential. Okay. So higher electrode potential is taken as a cathode and the lower electrode potential is taken as a, or the electrode is taken as a anode. So it becomes 0.34 minus of minus 0.76. So EMF of the Daniell cell, particularly if you use copper and zinc, I called it as Daniell cell, that is 1.1 volt. 1.1 electron volt. In this way, we can able to calculate the EMF of the cell. And what are the components that decides the EMF of the cell? The one is nature of the electrode, other one temperature, and the concentration of the electrolyte. See, I took this one is a 0.34. It mainly based when I use 1 molar solution of electrolyte. Electrolyte is a 1 molar, then only I can get 0.34. Otherwise, it may increase, usually it decreases. Clear? This is about the electromotive force of a cell. The difference of potential which causes the flow of current from an electrode of higher electrode potential to an electrode of lower electrode potential. Same way we can express standard EMF of the cell. It is the cell when all the reactant and products are unit concentration. I already discussed 1 molar concentration we took. Unit concentration or unit activity at 298 Kelvin and 1 atmosphere pressure. This I already discussed, the origin of single electrode potential. That is the metal movement of charge from the metal to electrolyte. So there is a development of electrical double layer. What we called it as a Helmholtz electrical layer, and that in turn gives the electrode potential. Yeah. Now I want to discuss what do you mean by a single electrode potential. Okay. So single electrode potential. See in the first slide I mentioned this one. Yeah. A metal is dipped in a metal ion solution. Okay. And develops this potential. And this potential, what we called it as single electrode potential. How it generates single electrode potential? When or the potential developed, where it developed, it usually developed at the interface between a metal and the liquid, or a solid and the liquid. And that potential, what we called it as a single electrode potential. That is the potential developed at the interface between the metal and solution. Where it develops? When you dip a metal, when the metal is in contact with the solution of its own ion. That is called as a single electrode potential. See, a zinc metal, if you take a zinc metal and dip in a zinc sulfate solution. Okay, I took zinc metal, dipped in a zinc sulfate solution. The potential developed, where it developed? It developed at the interface between metal and the solution. Okay. A single electrode potential is the potential developed at the interface between the metal and the solution. When it developed, when the metal is dipped in a solution, or when the metal is in contact with the solution of its own ion. Say Cu2 plus or a Cu metal, I dipped in a Cu2 plus solution. Then a potential 0.34 I observed, and that is called single electrode potential. A metal, it developed at the interface between a metal and the solution when the metal is in contact with the solution of its own ions. See, if I take a zinc metal and dip it in a copper sulfate solution, is it a single electrode potential, a potential generated by this? No, it is not a single electrode potential. Here, the metal is not dipped in a solution of its own ion. A different solution we use. That is, the potential developed is not considered as a single electrode potential. The basic thing is you have to take a metal which should be dipped in a solution of its own ion. At that time, at the interface, you can observe a potential called it as a single electrode potential. If you take 1 molar solution, in the case of zinc sulfate, if I take a 1 molar solution, then I observe some potential, and that potential, what we called it as a standard reduction potential. Okay, is the electrode potential when the electrode or the metal is in contact with the solution of unit concentration at 298 Kelvin. Okay, so that is called as a standard electrode potential. Okay, so take the next thing under engineering chemistry syllabus, that is a derivation of Nernst equation for a single electrode potential and related problems. Okay, I'll derivation. Nernst derive a quantitative relationship between electrode potential and the concentration of the electrolyte species involved. Okay, Nernst. So Nernst derived a single electrode potential equation, or derived possible you write this one because it would be better. You can and this one is a very important one. Am I audible?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Ma'am.
Okay. Relationship between electrode potential and concentration of the light solution. Okay, the basic that equation that relates the electrode potential. How we express the electrode potential? The electrode potential we express in terms of E, and that with the electrolyte solution, concentration of the electrolyte solution. If you can mention electrolyte solution involved during the reaction. To derive this one, first we consider a reversible reaction. Okay, consider a reversible reaction. Yeah. And you know, the reversible reaction means the forward reaction may be an oxidation reaction and the backward reaction may be a reduction reaction. So I'll take forward reaction is a oxidation reaction and the backward reaction is a reduction reaction, and I'll represent this way: Mn plus n number of electron. This is a well-known equation. I think you know very well. A metal ion dissolve in the solution forming a metal dissolve in the solution forming a metal ion with the liberation of n number of electrons. The forward reaction is oxidation reaction and the backward reaction is a reduction reaction. And you know very well known things like electrode potential is always represented in the form of reduction tendency, is it? So that's why by convention the electrode reaction, or you can take it a better way, is a reduction reaction. Electrode reaction is taken in the forward. Okay, as you can write it like this: as the electrode potential is the measure of reduction. How we write the reduction electrode potential? That is m n plus n number of electron giving rise to m, like Cu2 plus n number of electron giving Cu. This is what we call it as a reduction reaction. The next thing is we consider a thermodynamic equation, that is from thermodynamic consideration We can relate this equation with the equilibrium constant. Okay, the decrease in the free energy change is related to equilibrium. Which equation we use? This one, delta G minus delta G. I already mentioned here decrease in the free energy. Minus delta G is equal to minus delta G naught minus RT ln K. This equation you already studied one. Yeah. Minus delta G, the decrease in free energy change is related to equilibrium constant. Equilibrium constant. Okay, minus delta G equal to minus delta G naught plus, sorry, minus RT ln K. We can write this one in terms of delta G plus delta G equal to delta G naught plus RT ln K. Okay, what is this delta G naught? Delta G naught is standard free energy change. This is a standard free energy change when all the reactant and product are under standard condition in their unit activity. And what is this K? K is equal to an equilibrium constant. This equilibrium, how we express K for a reversible reaction? K, you just consider this reaction. How we write that Mn, this reversible reaction, Mn plus n number of electron giving rise to M. How we represent K? K is nothing but the product divided by reactant. So I can write it K equal to concentration of the product, that is M, by the concentration of the reactant, Mn plus. Okay, that is equilibrium constant. Now, or you can write if the electrode involves, what the function that takes place in the electrode, that is what is the function you observed in the electrode? It is a transfer of charge, is it? If the electrode potential is E volt, yeah, so consider it is a E volt, and there is a, and the electrode involves how many electron transfer observed? I'll take it as a general. Electrode reaction involves transfer of n electron. Thermodynamic consideration, that is the decrease in free energy of the system, which is related to equilibrium constant. And this decrease in free energy in turn that tells about the work that taking place in the system. If the electrode potential is E volt and the electrode reaction involves the transfer of n number of electron with, I'll take this one, with how much? With F Faraday's current passed in the electrode. So the work done by the electrode, now it becomes electrode is W is equal to NFE. Okay, this much of work that taking place, that is N is number of electron, F is Faraday's of current passed, is electrode potential of the electrode. Okay, now you know the decrease in free energy of the system, decrease in free energy change of the system is equal to maximum useful work done by the electrode or a system. So I can write you know W is equal to NFE, and you know the decrease in free energy delta G is equal to W, or you may write minus delta G is equal to NFE, or you may write minus delta G, or sorry, plus delta G is equal to minus NFE. I'll take this equation. I just observe the previous equation, you know, it is taken as 3, and now I'll take this equation 4. Okay. Now I'll take the one more for free energy, standard free energy delta G naught is equal to minus NF E naught for a standard electrode potential, and the equation I'll take it as a 5. Okay. Now I'll put equation 3, 4 and 5 in equation 1. So I can get, you know, first what I written delta G. Here delta G is minus NFE, that is equal to minus NF E naught plus RT. Here minus NF. Okay, the equation is same, plus RT ln concentration of M by concentration of Mn plus. Okay. Say I'll substitute equation 3, 4, 5 in equation 1, that is or equation 2, that is delta G equal to, better I'll take it as in equation 2. So minus NFE equal to minus NFE naught plus RT ln concentration of M by concentration of Mn plus. And here in both the side we observe a common term minus NF. So in the further state I'll just divide throughout by minus NF. Okay, if I divide by minus NF, the first we observe E, the remaining things is E equal to here minus NF I use, so it becomes E naught. Okay, and further here if I divide by NF, it minus NF, so the entire thing becomes, this term becomes minus RT by NF ln Mn. Okay, I'll put the same thing. Okay, see here I'll write, so it becomes minus RT by NF ln concentration of Mn plus. Clear? Concentration of Mn plus. Okay. See, the entire equation I divide by minus NF, so it becomes E equal to E naught minus RT by NF ln concentration of Mn plus. Okay. Or else, sorry, I was wrong. 1 minute, I'll put one more thing. So instead of that, I'll put as it is. Oh my God. Concentration of M by concentration of Mn plus. Clear? See here, in place of concentration of M, we can write it 1, because for solid, okay, concentration of M equal to 1. Okay, for all solid, the concentration is 1. You know, the concentration term appear only when it is a liquid, 1 molar, 2 molar concentration. For solid, we are not expressed in terms of concentration, or in usually expressed in terms of kg. Yeah, so that's why we'll take universally, we'll take it as a 1. So the equation becomes E is equal to E naught minus RT by NF ln 1 by concentration of Mn plus. Okay, say I can write this one like this: E is equal to E naught plus RT by NF ln concentration of Mn plus, or I may remove ln into log or change ln into log E naught plus 2.303 RT by NF log concentration of Mn plus. So here the electrode potential that relates with the concentration, and this is what we call it as a Nernst equation for a single electrode potential. Okay, it is a Nernst equation for a single electrode potential. This is the derivation what we observed. Okay, Nernst equation for a single electrode potential. So you may write at the 25 degrees Celsius, you know, R is equal to 8.314 joule per Kelvin per mole, and F is 96,500 coulomb, and temperature 25 degree we may express is equal to E naught plus 2.303 into 8.314 into 273. 25 means it, if it were expressed in terms of Kelvin, it's 273. 10 into 96,500. And then what? Log concentration of Mn plus, or finally we'll get E is equal to E naught plus 0.0591 by N log concentration of Mn plus. This is equation. We may use this equation also when the problem is given at 25 degrees Celsius. This equation is used when the reaction that taking place at 25 degree Celsius. This is what we called it as a Nernst equation for a single electrode potential. Okay. I'll just briefly explain it again. Okay. So Nernst derive a quantitative relationship between the electrode potential and the concentration of the electrolyte solution involved. Yes. Anyone want to ask anything? Okay. For that purpose, he taken a consider a reversible reaction, M giving rise to Mn plus plus n number of electron. This is nothing but you may consider like a reaction like C, or I'll take a reaction like Zn2 plus giving rise to, or better I'll take Zn oxidation. Okay. Say Zn giving rise to Zn2 plus plus 2 electron. This is oxidation reaction, you know. So if you take in a reverse order, it becomes reduction reaction. In general, I took M giving rise to Mn plus plus n number of electron, because while expressing the or deriving the equation, you have to take a general term. So M giving rise to Mn plus plus n number of electrons. Reversible reaction is considered. And you know, the electrode potential is always expressed in terms of reduction tendency. So that's why, or the reduction electrode potential. How we represent electrode potential? E Zn2 plus bar Zn. That is electrode, zinc electrode, reduction potential of zinc electrode, we express it like 0.76 minus 0.76 volts. That means we have to consider the reduction reaction. So that's why I'll take, by convention, the reduction electrode reaction is taken in the forward direction, as the electrode potential is the measure of reduction tendency. So that's why I'll write Mn plus n number of electrons giving rise to M. Okay. Then I'll take one more equation that relates the free energy change with the equilibrium constant. That is by the equation delta G minus delta G equal to minus delta G naught minus RT ln K. From thermodynamic consideration, the free energy change of the system is related to equilibrium constant by an equation minus delta G equal to minus delta G naught minus RT ln K. Or changing the sign, we'll get delta G equal to delta G naught plus RT ln K. Okay, what is this delta G? Delta G is a free energy change. And what is delta G naught? It is a standard free energy change when all the reactant and the product of the reaction under standard condition. And what is K? K is an equilibrium constant. That is the product by reactant. K is equal to concentration of M by concentration of Mn plus. Okay. Then what is the reaction that taking place in the cell? So or electrode, it is the if the electrode potential is E volt and the electrode reaction involves a transfer of n number of electrode with the potential of with the F Faraday's current passed, then work available from the electrode is W equal to minus NF E. Or in other words, we can consider like the possible work that is observed in the electrode is the transfer of NF coulomb of charge with the potential of E volt. So we can write W equal to minus NF. The decrease in free energy change of the system is equal to electrical work done of the system. Work that taking place in the electrode is nothing but the transfer of electrons. So we can write it as delta G equal to W, or in other words, minus NF E. Delta G equal to minus NF E. Okay, delta G is equal to minus NF E, or we can write it as W is equal to minus delta G, or equal to delta G equal to minus NF E. So delta G is minus NF E, delta G naught is minus NF E naught. Now I know the three equation. The one is equilibrium constant, another one is delta G, another one is delta G naught. And these three equation I'll substitute in the equation number 1. Okay, that is the Gibbs equation. So I can write delta minus NF equal to minus NF E naught plus RT ln concentration of M by concentration of Mn plus. Okay. So then the entire thing is divided by minus NF, not plus. I'll take minus NF. So minus NF E divided by minus NF. That becomes E. So E equal to E naught minus RT by NF ln concentration of M by concentration of Mn plus. And I know concentration of this M is equal to 1 because it is a solid. For all solid, the concentration is 1. So we can write E is equal to E naught minus RT by NF ln 1 by concentration of Mn. So I know the ln 1 by A, or this one, 1 by A is equal to minus ln A. Okay, I use this equation and I'll put it here. Minus ln 1 by A is equal to plus ln A. I'll convert this 1 by concentration of ln 1 by concentration of Mn plus into minus ln concentration of Mn. So the equation becomes E is equal to E naught plus minus of minus becomes plus RT by NF ln concentration of Mn plus. So I'll change ln into log. So the final equation becomes E is equal to E naught plus 2.303 RT by NF log concentration of Mn plus. This is a Nernst equation for a single electrode potential. At 25 degrees Celsius, we substitute, the all R, F are constant. We'll put the constant term and finally we'll get E is equal to E naught plus 0.0591 by N log concentration of Mn plus. Okay, is it clear? Derivation part. Single electrode potential. Nernst equation for a single electrode potential. Any doubt? Please unmute yourself and answer me. Any doubt? Am I audible?
Yes, ma'am.
Is it clear?
Yes, ma'am.
Okay, is it clear? Any doubt? Yes, any doubt?
No, ma'am.
It's clear?
No, ma'am.
See, somebody written in the chat box G equal to minus NFE, but not G. It is the change in free energy equal to minus NFE. Okay, we usually consider change in free energy. In all reaction, there is a small change in the free energy. So that's why here also the decrease in the free energy change we consider. And sometimes they written like a decrease in free energy. If I write free energy, I should write it as a G. But here in the equation, what we observed is a delta G. So decrease in free energy change. Okay. In some book, they represented just a free energy of the system. But actually, it is a change in free energy of the system. Okay. This it is for a single electrode potential, say zinc electrode or a copper electrode. Like if you want to express a cell, okay, if you want to express the cell potential, then I'll consider a reversible reaction. Okay, like for a cell potential, I'll take A. This is a one cell reaction, EB, giving rise to E of C plus E of C. Like Zn giving rise to Zn2 plus here Cu2 plus Cu. Clear? This is type of reaction. Instead of writing this reaction, I'll generalize this one. If you consider for a cell reaction, if you want to write a Nernst equation, if you derive, you will get this type of equation. Say here we write E, but here I should write E cell because it is for cell reaction. Okay, E cell equal to E naught cell. Okay, either I can take a plus sign or minus sign based on or depending upon this one, log which type of species I took. Okay, log. I'll take minus 2.303 RT by NF log concentration of C to the power C, E to the power D divided by A to the power A. What is this C to the power C, D to the power D? This term, yeah? What I observed, the term like. And what is this species in the galvanic cell? What type of species is one? How it is generated? The zinc ion. Anyone, unmute yourself and tell. How zinc ion generated? Please tell me. See, this is a general equation. I took Zn plus Cu2 plus giving Z to Zn2 plus Cu. Okay. Here, C and D, this related to these terms. Okay. That is Zn2 plus concentration of Zn2 plus into concentration of Cu. Cu, it is a metal. The concentration is 1. Okay. That is concentration is considered as a 1. And Zn is the concentration of oxidation species. Like divided by concentration of A to the power A. That is Zn. Again metal. It's a 1. And Cu2 plus, that is a reduction species. So in general, we may represent this way: E naught cell minus 2.303 RT by NF log concentration of oxidation species by concentration of reduction species. This is mainly we use to express the cell potential. Okay, E cell equal to E naught cell minus 2.303 RT by NF log concentration of oxidation species by concentration of reduction species. Or you may write it in another way. The term log concentration of oxidation species by reduction species. If you reverse it, if you can take the numerator term denominator and the denominator term, if you take it to a numerator, so it becomes negative log of oxidation species, reduction species by oxidation species. So negative log of that one multiplied by negative 2.303 RT becomes positive. Or you may express in another way, that is I'll put it here only. Okay, and another way you can represent E cell equal to E naught cell plus 2.303 RT by NF log concentration of reduction species by the concentration of oxidation species. There. See, here I took a positive sign. If you took a positive sign, the reduction species should be in the numerator. Okay. If you take a negative sign, it should be in the numerator. Okay. Sorry, it should be in the denominator. Okay. See, this is the equation used to derive a cell potential, or the cell potential equation that relates with the electrolyte species anode. Here, this is about the Nernst equation for a single electrode potential. Say, I'll write the Nernst equation for a single electrode potential E equal to E naught plus 2.303 RT by NF log concentration of Mn plus. Okay. So this is single electrode. For cell potential, E cell equal to not cell plus 2.303 RT by NF log concentration of reduction plus concentration of oxidation species. I think you know this. Here, a cell means there is involvement of two species. Yeah. In the case of cell like Zn, giving rise to Zn2 plus 2 electron, Cu2 plus 2 electron, giving rise to Cu. Okay. So net cell reaction Avirise Cu2 plus giving rise to Cu plus Zn2 plus this way. Whereas in the electrode, you simply take the one electrode, Zn giving rise to Zn2 plus 2 electron, or in a case Cu2 plus 2 electron giving rise to Cu. The potential developed by a single electrode equation is equal to naught plus 2.303 RT by NF log concentration of Mn plus. For cell potential, Ecell equal to naught cell plus 2.303 RT by NF log concentration of reduction species by oxidation species. Is it clear? Any doubt under this? And you know what are the things or electrode potential depends on? The electrode potential depends on temperature and the concentration of the ions, and even it depends upon nature of the electron, number of ions involved, electrons involved, nature that defines the nature of the, it depends on nature of the electrode. Okay, this is about the derivation part of Nernst equation. Okay, say, I think it is clear. Any doubt under this Nernst equation? And this is a very important one. Any doubt? Any doubt? Please unmute yourself.
Ma'am, I did not understand it.
Which one?
Nernst equation derivation at last part.
Here we took a reversible reaction. I'll explain the entire thing. Okay, a reversible reaction, that is a reversible reaction, that is metal gives metal ion plus a number of electrons. A reversible reaction, forward reaction is the oxidation, backward reaction reduction. But electrode reaction is, or electrode potential, usually expressed in terms of reduction tendency. So that's why I'll take a metal ion takes electron, giving metal as a forward reaction. Okay. Then I consider one thermodynamic equation. That equation that relates the free energy change with the equilibrium constant. That is minus delta G is equal to minus delta G naught minus RT ln K. Okay. RT ln K. So what is delta G? Delta G is the change in free energy. Okay, or the free energy change. What is the free energy change you observed in the electrode is nothing but that maximum useful work available from that electrode. And what type of work is observed in the electrode? That is a transfer of n number of electron with F Faraday of current, which carries F Faraday of current with a potential of E volt. Clear? An electrode always possesses some potential that depends upon the nature of that electrode. Okay, say zinc electrode, it possesses minus 0.76 potential. Okay, and it can able to generate a electron, 2 electron, and that electron is transferred to an external circuit. That is a work that observed in that electrode, and that is nothing but the free energy that involves in the decrease in free energy, which relates to the maximum useful work that taking place in the system. That is, if an electrode potential E volts, that involves a transfer of n number of electron with the F Faraday of current, okay, then a maximum useful work that is available from the work can be expressed as W equal to minus NFE. Why we write minus? Because you know the decrease in free energy minus delta G, that is equal to W. you already known the decrease in free energy of the system is equal to maximum useful work available from the system minus delta G is equal to W. So what is W? W is equal to, okay, I was wrong this one, I'm sorry. This W is nothing but W is equal to minus delta G. Sorry, W is equal to minus NFE and minus delta G is equal to W. So we can write it as minus delta G equal to NFE, or delta G is equal to minus NFE. Delta G is equal to minus NFE. Clear? And delta G naught is equal to minus NF E naught. So the equilibrium, these two equations or three equations, we put it in the equation number 1. We can get minus NFE equal to minus NF E naught plus RT ln concentration of M by concentration of Mn plus. Okay. So the entire equation should be divided by minus NF. So we can get E is equal to E naught minus RT by NF ln concentration of M by concentration of Mn plus, or we can write it as E is equal to E naught plus 2.303 RT by NF log concentration of Mn plus. Okay. Clear? Previously what I written, I directly took this one, W is equal to minus NFE, but it is a decrease in free energy change is equal to W, and W is equal to NFE, or we can write it as minus delta G is equal to NFE, or delta G is equal to minus NFE. Okay. Today's topic, that is problems on single electrode potential and cell potential. Okay. First problem, I'll take this one. Calculate the E naught. Okay. Calculate the E naught of zinc electrode. It is usually represented this way: E naught Zn2 plus bar Zn. Okay. Calculate E naught Zn2 plus bar Zn for the reaction. That is, here what we observe is a reduction reaction. For the reaction, Zn2 plus 2 electron giving rise to Zn at 25 degrees Celsius. What is given? Given is E naught Zn 2 plus bar Zn equal to minus 0.76 volt, and Zn2 plus concentration is 0.1. For this concentration, at this concentration, you have to calculate electrode potential, not E naught, it should be E. Okay. First, I'll take a Nernst equation. Okay. So, Nernst equation for a single electrode potential. I know E equal to E naught plus, here they mention 25 degrees Celsius. Okay. That's why directly I can take 0.05, both 59, in some book you can observe 592, in some book some 591. Okay. N log concentration of Mn plus. Okay. Now E naught is given. Yeah. E naught Zn2 plus bar Zn is given. That is equal to minus 0.76 volt. Okay. Then Zn2 plus concentration is given, that is 0.1 M. Okay. You have to substitute this in the equation. So E equal to, here it is given minus, I'll write 0.76 plus 0.0592 by N. How many electron transfer we observe here? N equal to 2. N equal to 2 divided by 2 log concentration, that is 0.1 M, or I'll write just 0.1. Okay. I can write it as just a 0.1. Okay. Then how to find 0.1 log of 0.1 minus 0.76 plus 0.0592 divided by 2 is nothing but 0.0296, and log 0.1 is nothing but minus 1. So what is the value you get? E of Zn2 plus bar Zn electrode potential of zinc electrode at 0.1 m concentration becomes minus 0.7895 volt. Okay, them is this, and you try to write these things. Okay, you have to submit all these problems. So that's why simultaneously while solving you write it, and even you use calculator, and you should answer it. Okay, next, this is the first one, so that's why I'll directly myself I write the answer. Otherwise you have to answer. Okay, calculate and answer it. Okay. The second problem, the standard electrode potential of zinc electrode is minus 0.76 volt. What will be the potential of 2m solution at 300 Kelvin? Okay. What is the difference you observed between the previous and this one? In the previous problem, they mentioned at 25 degrees Celsius. So you can use equation, standard equation at 25 degrees Celsius. But here, the temperature is different. That is 300 Kelvin. And in the previous problem, they given the concentration is 0.1 mole. Here, here it is 2 molar. Okay. Say, I'll take the general equation. Usually, while solving the problem, first you have to write the equation. So, I'll take general. For general equation, you can write it like this. Mn equal to E naught Mn plus bar Mn plus 2.303 RT by NF log concentration of Mn plus. I'll substitute known things. They given the standard electrode potential minus 0.76 plus 2.303 into, and you know the R value is R is nothing but 8.314 into temperature 300 divided by n number of electron. What is this electrode we use? Zinc electrode. So zinc electrode takes 2 electron. Okay, Zn2 plus takes 2 electron, giving Zn. So n equal to 2. Okay, I'll take 2 here, n into 96,500. Okay, log concentration of 2. Okay, see how much it becomes. Minus 0.76, 0.02976. Yeah, is it right?
Yes, ma'am.
Okay. Now final one. Final minus minus 0.750 volt. This is the potential developed when you use a 2 molar solution. Okay, when you use a 2 molar solution, you will get, this is the final correct answer, 0.7570. Okay, 0.7570 volt potential is developed. Next, I'll take next problem. This both we arrive solve the problem based on a single electrode potential. Okay. Now I'll take cell potential. How we solve the problem related to a cell potential. Okay. Here a cell uses zinc Zn2 plus bar Zn. A cell uses Zn2 plus bar Zn and Ag plus bar Ag electrodes. Write cell representation, half cell reaction and net cell reaction. calculate the EMF of the cell, here given thing is E naught Zn2 plus bar Zn equal to 0.76 volt and E naught Ag plus bar Ag equal to 0.34 volt. Okay. Here they given not only to calculate Ecell, you have to write the cell representation, half cell reaction and net cell reaction. Okay. First, you have to find among the two electrodes, which one act as anode and which one act as a cathode. The given thing is E naught Zn2 plus per Zn is minus 0.76 and the silver electrode potential is 0.34 volt. Okay. The higher the reduction potential, here the reduction potential of Ag electrode is high. Yeah. See, reduction potential of Ag electrode is high, so it is taken as, or it act as cathode. Okay, you already know the one which possesses a higher electrode potential act as cathode, and the other electrode, zinc electrode, act as anode. So we can write, based on this, we can write the cell representation. We can write the cell representation, where first we have to write a anode, that is Zn giving rise to Zn2 plus 2 number of electrons. So that's why first we write the anode representation, zinc bar Zn2 plus. Here the single vertical line indicates the phase change. Okay. Then you have to write the double vertical line, that is the salt bridge. Double vertical line is the salt bridge. The two electrode is connected by means of a salt bridge. And then you write the cathode representation, that is silver electrode Ag plus bar Ag. Okay. First anode, then cathode. And you know, here they are not mentioned the electrolyte concentration. Usually in the cell will take aqueous solution of this electrolyte. It's a simple way representation of electrode. First you have to write an anode. Okay. First write anode electrode, then cathode electrode, then cathode electrode. And these two electrode is connected by means of a salt bridge, represents by means of a double vertical line. This is a representation. Now I'll take the next thing, that is you have to write the half cell reaction. So the first you write at anode, what is the reaction take place? That is oxidation. Zinc giving rise to zinc ion with the liberation of 2 moles of electron. Okay. At cathode, what is the reaction? That is reduction reaction. So reduction reaction, that is Ag plus ion takes electron giving rise to Ag. Here silver can able to give only 1 electron. Okay, the state is so that it can take stability. But zinc 2 electron can able to give. Okay, so that's why while writing the silver, you have to write a single electron. But it is a spontaneous redox reaction. So the second equation should be multiplied by 2. Okay. Number of electron transfer, or the number of electron liberated, should be equal to the number of electron consumed at cathode. So that's why the second equation should be multiplied by 2. Now the next question is you have to write the cell reaction. So the sum of this is nothing but a cell reaction. Okay, that is cell reaction. Zn plus 2Ag plus, I have to multiply second equation by 2 and this becomes 2 electron get cancelled. Zn2 plus 2Ag. This is a net cell reaction. Now, the final thing you have to calculate EMF of this cell, electromotive force of the cell. EMF equal to E naught cathode minus electrode potential of cathode minus electrode potential of anode. And you know the which electrode act as cathode? That is silver. So can write E naught Ag plus bar Ag minus E naught Zn2 plus bar Zn. And E naught Ag plus, you know, it is point, again it is wrong given. Here, you just take change in the this one. It is not 0.34, it should be 0.8 volt. Okay, in the problem itself it's wrong. It is 0.8 minus of minus 0.76. Okay, so 0.8 minus of minus 0.76, it becomes 1.56. Here I'm not taking any Nernst equation. Here directly I arrive the cell potential based on the standard electrode potential of zinc electrode and the silver electrode. Clear? See here what I taken is why I am not taken Nernst equation, because they are not mentioned the electrolyte concentration. If they mention the electrolyte concentration, then that electrode potential or the cell potential that depends upon the electrolyte concentration. But here I'm not taken electrolyte. I'm not consider electrolyte because they are not mentioned. Clear? See in this problem, they given the two electrodes. First, you have to write the cell representation. Silver and zinc electrode given. Silver electrode potential is high compared to zinc electrode. So that's why it is taken as a reduction electrode. So cell representation is zinc giving rise to Zn2 plus, or you can write it as cell represent Zn bar, Zn2 plus, double bar, Ag plus bar, Ag. At the anode, oxidation takes place. So Zn giving rise to Zn2 plus 2 electron. At cathode, Ag plus electron giving rise to Ag. So here it is a simultaneous reaction. The number of electron liberated is equal to the number of electron consumed. So it should be balanced. So that's why the cathode reaction should be multiplied by 2. So the final cell reaction is Zn plus 2Ag plus giving rise to Zn2 plus 2Ag. Next step, you have to calculate the cell potential. EMF of the cell is equal to E naught cathode minus E naught anode. Here cathode is a silver electrode and anode is a zinc electrode. So silver electrode potential is 0.8 volt and the zinc electrode potential is minus 0.76 volt. So the net EMF developed by the cell is 1.56 volt. Okay. Is it clear? Any doubt? Representation of a cell, then reaction, anode reaction, cathode reaction, or selection of anode and selection of cathode. Any doubt? Any doubt? Please answer.
No, ma'am.
Huh? It's,
No,
it's
ma'am.
clear. Okay. I observed box. Okay. Now one question. Next problem. That is related to cell potential, Nernst equation, or the determination of cell potential. Okay. Here, calculate the cell potential for the following cell. That is, ion interact with the cupric ion forming ion, ferric ion plus copper. When cupric ion concentration is 0.3 m and Fe2 plus ion concentration is 0.1 m, given E naught cell is 0.73 volt. You have to calculate cell potential. Okay. Here, what are the things given? They given the cupric ion concentration and the ion concentration. Okay. But they are not mentioned the electrode potential of copper and the electrode potential of iron. Okay. The copper electrode potential is 0.34, whereas iron electrode potential is minus 0.44, I think it's volt. So iron electrode potential is less compared to copper electrode potential. So iron act as anode and copper electrode act as cathode. Okay. So here you can write Fe electrode act as anode and Cu electrode act as cathode. This is completely based on the reduction potential of the two electrode. Okay. Next, I'll write the Nernst equation for a cell potential. Okay. E equal to, or E cell equal to E naught cell. I'll take minus sign. Okay. Minus. And at 25 degree, I'll mention, because they are not mentioned the temperature. So I'll take for 25 degree, 0.0591 or 2. In some book they given 2 by N log concentration of the product by the concentration of the reactant, Fe2 plus, or you can write it as a product by the concentration of the reactant. Or you may represent this one is a concentration of the product means oxidation species divided by, that is, reduction species, because here I took negative sign. Okay. Now E naught cell is given, that is 0.73 minus 0.0592. How many number of electron transfer observed? Number of electron transfer is 2. Yeah. Here 2 electron is observed. Here also 2 electron. Number of electron transfer is 2 log product Fe2 plus ion, that is 0.1 divided by 0.3. Okay. Log of 0.1 divided by 0.3, you can get some numerical values. Log of that one you find out. Okay. Then multiply by 0.0592 by 2. Okay. 0.73 minus 0.0296 log 0.1 by 0.3. Okay. See, you will get after this, you can get, I think, 0.8 volt potential. Okay. That is Ecell. This particular this cell, you will get 0.8 volt of potential. Okay. In this way, you can able to calculate the cell potential. Any doubt under this? Any doubt? Any doubt? Okay. Next, I'll take similar type of problem. I'll take the similar type of problem. That is, what is the cell potential of the electrochemical cell in which the cell reaction is Pb2 plus cadmium giving rise to Pb plus cadmium ion. Given that E naught cell is equal to 0.277 volts. Temperature given is 25 degrees Celsius and cadmium ion concentration is 0.02 m and the lead ion concentration is 0.2 m. Here, from this cell reaction itself, you can predict anode and cathode. Even in the previous problem, from this cell reaction, you can predict anode and cathode. Here, the cell reaction, you can see Pb2 plus, okay, giving rise to Pb. That means it should consume 2 electrons. Yeah. And the second thing is Cd giving rise to Cd2 plus. That means by giving 2 electron, it converted to Cd2 plus. Okay. So the Pb consume electron. That means it acts as cathode. Yeah. Cadmium gives electron. So act as anode. Clear? So this way you can predict the anode and cathode. Anode and cathode. Now I'll take a simple cell Nernst equation. E cell is equal to E naught cell. Here I'll just change. I'll take a positive sign. In the previous case, I took a negative sign and I calculated. Here positive sign. If you take a positive sign, then reduction species comes to numerator. Okay. 0.0592 by N log concentration of reduction species, that is reactant, by the concentration of the product, that is oxidation species. Okay, this way. Now I'll substitute the values. 0.2, how much it is? 0.277 plus 0.0592. Number of electron transfer is again 2. Log concentration of reduction species. The reduction species is lead. Yeah, and reduction species is lead. I'm again confused. Okay. Oxidation species is a cadmium. Lead is a reduction species and the cadmium is an oxidation species. So lead concentration is 0.2 divided by 0.02. Is it right? Clear? Clear? See here, I took a positive sign here. So that's why numerator term reduction by oxidation. The reduction species is a lead. Oxidation species is a cadmium. Okay. Now, that equal to 0.277 plus 0.0296. Okay. How much it becomes? Log of, calculate. 1. How much? 10. Log 10 is? How much? Log 10 is 1. So you can get like this 0.277 plus 0.0296. So the final answer is Ecell equal to 0.3066 volt. Okay, this is the final answer. Observe. Okay. Now I shall move to the next problem. That is, an electrochemical cell consists of magnesium electrode in 0.084 m magnesium nitrate solution. That is, magnesium metal is dipped in a 0.084 m magnesium nitrate solution, and silver electrode, electrode means silver metal, is dipped in a 0.70 m AgNO3 solution. The standard electrode potential of Mg and Ag are minus 2.363 volt and plus 0.80 volt respectively. Represent the cell, write the cell reaction and calculate EMF of the cell. Okay, here the given the electrode potential of the two electrodes, magnesium electrode and the silver electrode. See, what is the given thing is E0 Mg2 plus bar Mg is given, that is minus 2.363 volt, and silver electrode E0 Ag plus bar Ag is 0.8 volt. Okay. Among the two electrodes, silver electrode possesses a higher electrode potential. Okay. See, Ag electrode act as cathode. Why? Because it is a high electrode potential, and Mg electrode act as here. Now you already predict which one acts as anode and which one cathode. Now you represent the cell. Okay, representation. See, first you have to write the anode Mg2 plus bar Mg, double bar Ag plus bar Ag. This is a cell representation. Now you have to write the cell reaction. While writing the cell reaction, before you have to write the half cell reaction. Anode, at anode, the anode is a which one? Magnesium, Mg, giving rise to Mg2 plus 2 electron. Okay. At cathode, that is Ag plus electron, giving rise to Ag. This the second equation should multiply by 2 because simultaneous reaction. So you can get Mg plus 2Ag plus giving rise to Mg2 plus 2Ag. Okay, now already written the cell representation. Now you have to calculate EMF of the cell at the two different concentration. The magnesium electrolyte is 0.084 and silver electrolyte is 0.70 molar. Okay, at this for this concentration you have to calculate the electrochemical cell potential. So for that you have to write the Nernst equation. Ecell equal to E naught cell. Okay, Ecell equal to E naught cell plus 0.0592 divided by n log concentration of reduction species by the concentration of oxidation species. Okay. See, E naught cell is nothing but E naught Ag plus bar Ag minus E naught Mg2 plus bar Mg. Yeah. Plus 0.0592 by n log concentration of reduction species. Which one is the reduction species here? That is silver. Yeah, I'll take concentration of Ag plus to the power 2. Why I represent to the power 2? Here, if you observe the reaction involves the involves the 2 number of electron. Here you mentioned the 2 Ag to the power 2, Ag plus to the power 2 you have to mention. Clear? That's why I'll take here Ag plus to the power 2. And you know the electrode potential of silver electrode 0.8 minus of minus, that is 2.363 plus 0.0592 number of electron transfer to log concentration of Ag plus ion, that is 0.7 to the power 2 divided by this one is 0.084. Either you can write log a to the power 2 a to the power a square by b or 2 log a by b. Okay, anyway you can write it. So here this value we can get 3.163 plus 0.0296. Okay, then log of this log of 0.7 to the power 2 divided by 0.084. After calculation we'll get Ecell equal to 3.1856. You just use calculator and calculate it. You just make the practice, otherwise it is difficult. Okay. Log 0.7 to the power 2 divided by 0.084. For the value you get, find the log, multiply 0.0296, add 3 point to that, add 3.16, 3 will get 3.1856 volt. Okay. See here in this cell you are given 2 electrolyte concentration. Magnesium electrolyte concentration is 0.084 and silver electrolyte concentration is 0.70. Then standard electrode potential of magnesium is minus 2.363 and the silver is 0.8 volt. Represent the cell. So Mg2 plus bar Mg double bar Ag plus bar Ag. And here better you can write the electrolyte concentration. Mg is 0.084 and here silver is 0.7. Okay, electrolyte representation. Then at anode oxidation, Mg we giving rise to Mg2 plus 2 electron. At cathode reduction, Ag plus electron giving rise to Ag. So the net cell reaction is Mg plus 2 Ag plus giving rise to Mg2 plus 2 Ag. Then cell potential, Nernst equation, E naught cell, E cell equal to E naught cell plus 0.0592 by n log concentration of reduction by concentration of oxidation. When you write reduction species in the numerator, you have to take positive sign in the Nernst equation. If you take the oxidation spaces in the numerator, then you have to take negative. Here you can get the final answer is 3.1856 volt. Okay. Any doubt under this? Any doubt? Any doubt? Okay.
No,
Thank you. Next class I'll
No, ma'am.
okay. Okay, next class I'll continue and take the remaining few problems, okay, related to Nernst equation. And soon I'll upload this one as well as the previous one video, okay. And I'm not send any link to your or the group. You just go through that my YouTube channel and watch that one, okay. Thank you. Take the problems on single electrode potential and cell potential. Okay. Yeah. This problem is similar to the previous discussed problem. One, only the change in concentration is observed. Anyway, I'll take it this one once again. Here, a electrochemical cell is formed by consisting of a magnesium electrode, which is dipped. That metal is dipped in a 0.042 m magnesium hydride solution, and silver electrode in 0.35 m AgNO3 solution. So standard SEP means standard electrode potential of magnesium and zinc are minus 2.363 volt and 0.8 volt respectively. Represent the cell, write the cell reaction and calculate the EMF of the cell. You already know how we represent this cell. So while representing the cell, first you predict which electrode acts as anode and which one as cathode. Here, the silver electrode possesses a higher electrode potentials. See, Ag1 electrode that possesses a higher, that is 0.8 volt, whereas this minus 2.363. So silver electrode, that is Ag electrode, now act as cathode. You know, it possesses a higher electrode potential than Mg electrode. Yeah. So that's why silver electrode acts as anode. And now I consider the cell representation. How we represent the cell? So first you have to write a anode Mg bar Mg 2 plus. What is the electrolyte concentration of Mg? That is 0.042 m. The two electrodes separated by means of a salt bridge. Then cathode is Ag plus, where the electrolyte concentration is 0.35 m bar Ag. Now I can write the reaction. At anode, half cell reaction, anode Mg giving rise to Mg2 plus 2 electrons. So at cathode, that is Ag plus, that you know, it takes only one electron at a time. So we write it as a Ag plus plus electron giving rise to Ag. Simultaneous process, so that's why the second equation should be multiplied by 2. Now the cell reaction becomes Mg plus 2Ag plus in raised to Mg2 plus Ag. These are the second part, that is representation of a cell, cell reactions and half cell reaction. Now you have to calculate the EMF of the cell. Okay? To calculate the EMF of the cell, you have to take a Nernst equation. And you know the Nernst equation, how we represent Ecell equal to E naught cell, yeah, plus 0.592 by n log concentration of reduction species by the concentration of oxidation species. And E0 cell, how we calculate? That is using the two electrodes. Silver electrode potential is 0.8, okay, minus of this one magnesium electrode. That potential is minus 2.363. I'll take the same one, minus 2.363 plus 0.0592 by number of electron transfer is 2, okay. Then log reduction species concentration is silver ion concentration is 0.35, but while writing it should be the power, okay, because 2 electron transfer is observed, divided by magnesium ion concentration 0.042. Okay, now here 3.163 plus 0.0592 by 2. I'll take it as a 2 log. Okay, 2 log 0.35 divided by 0.042. Okay, so that is equal to 3.163 plus 0.0592 and log of 8.3. The final answer before the step 163 plus 0.0592 into log of 8.3 we get 0.9206. So Ecell becomes equal to 3.2175 volt. Okay, this is the final answer that we get. So Nernst equation we introduce Ecell equal to E0 cell plus 0.0592 by N log reduction species by oxidation species. E0 cell is E right minus E left. Right electrode is a silver electrode, so 0.8 minus of minus 2.6363 plus 0.0592 by 2 log concentration of the silver ion, that is 0.35 to the power 2, because the reaction involves the transfer of 2 electrons. Then the final answer what we get is, after substitutions we will get Ecell equal to 3.2175. Okay, now I'll take the next problem. A cell is formed by dipping zinc rod in 0.01 m zinc sulfate or a Zn2 plus solution and nickel rod in 0.5 m Ni2 plus solution. The standard electrode potential of zinc and nickel are minus 0.76 and minus 0.25 volt respectively. Write the cell representation, cell reaction, and calculate the EMF of the cell. Okay. Here, similar to this problem is similar to the first one. Okay. Here, they given the 2 electrode potential. First, you predict which electrode acts as anode and cathode. Both poses a negative potential, like minus 0.076 and minus 0.25 volt. So now you find among the 2 electrodes, which electrode possesses a higher reduction potential? Minus 7.5 or minus 2.5. Which one is a higher electrode potential in this negative scale? This is a minus 0.25 near to 0 positive, and this is a minus 0.76. Yeah, that means here near to positive means this is a highest that the electrode potential is high. Yeah, nickel possesses a higher electrode potential, whereas the other zinc possesses a less electrode. Nickel now nickel electrode, that you know why it acts as an anode electrode. Sorry, why it acts as as possess a higher reduction potential. Higher. That's why it is taken as N. Once you know the electrode, cathode, and anode, you can able to represent the cell. Okay. Representation. First, you write anode. That is sudden bar, sudden 2 plus. They given the concentration, so I'll mention 0.01. Double bar. Then Ni2 plus. Concentration is 0.5 m. Then anode reaction at anode, that is familiar one, zinc giving rise to 2 electron converted into zinc ion. At cathode, Ecell takes 2 electron. Net cell reaction, sudden plus. Now is it clear? Sudden plus Ni2 plus giving rise to sudden 2 plus plus Ni. Okay. This is a net cell reaction. Clear? This is a net cell reaction. Now the next one thing is you have to calculate EMF of the cell. Am I audible? Can you confirm? My slide is visible. My voice, is it clear?
Yes, ma'am.
Yes, ma'am.
Hmm?
Yes, ma'am.
Next, you have to calculate EMF of the cell. Use Nernst equation. Ecell equal to E naught the cell plus 0.0592 by N of concentration of reduction species by the concentration of oxidation species. That is E naught cell we can calculate using the 2 electrode potential minus 0.76, okay, plus 0.0592 by 2 or 0.5 by 0.51 plus 0.0, or I can write directly 5.3. This terms comes to the total comes 0.0503. So Ecell is 0.5603. And this way we can able to calculate the cell potential of the cell. Now I'll take little different types of problem. Next I'll go into a different type of problem. Okay. So in this problem, you have to calculate the zinc electrode potential. For that, they given the EMF of the cell. 2 cells they construct. Their EMF is given. The one cell is constructed using zinc electrode and nickel electrode. Their potential developed is 0.51 volt, and the cell which is constructed using nickel and standard Calomel electrode, their potential is 0.49 volt. The question is you have to calculate zinc electrode potential. Like calculate zinc electrode potential. E naught Zn2 plus bar Zn. That means zinc electrode potential. If the EMF of this cell, that is zinc coupled with a nickel electrode, which develop 0.5 volt, and nickel if coupled with a standard Calomel electrode, the potential developed is 0.49 volt. The given thing is the standard Calomel electrode potential is 0.24 volt. Okay. They are not directly given the nickel electrode potential. Okay. In the first phase, you can observe. If you know the nickel electrode potential, then only you can able to calculate zinc electrode potential using a standard equation, that is Ecell equal to E naught cathode minus E naught anode. By using this equation, you can able to calculate the either cathode electrode potential or anode electrode potential or a cell potential. Okay, the two terms you should know. Here you have to calculate nickel electrode potential provided if you know the zinc electrode. Sorry, you have to calculate zinc electrode potential provided if you know the nickel electrode potential. But to calculate nickel electrode potential, they given one more cell that develops a potential of 0.49 volt. That cell is constructed using nickel and standard Calomel electrode. From this cell, you can able to calculate nickel electrode potential. Okay, the first step is to calculate E. Okay, I'll take a standard electrode potential, that one E Ni2 plus bar Ni. Okay, how to calculate this one? Standard electrode potential of nickel electrode, and you know the equation cathode minus anode, so we can write E cell equal to cathode is E naught. In this cell, the cathode is standard Calomel electrode minus E naught Ni2 plus bar Ni. And you know the standard Calomel electrode potential 0.24 minus E naught Ni2 plus bar Ni equal to E cell, that is 0.49. Okay, 0.49. Now E naught Ni2 plus bar Ni becomes equal to 0.24 minus 0.49, that is equal to minus 0.25 volt. Now, you know the nickel electrode potential. You know the EMF of this cell, okay? You know the EMF of this cell, that is 0.51 volt, and nickel electrode potential. You can able to calculate, now you can able to calculate zinc electrode potential. The next step is to calculate E naught Zn2 plus bar Zn. Okay, now we calculate there. We take a cell, this one E cell. Now E cell equal to the, find out the anode electrode and cathode. Cathode is nickel, yeah. E naught Ni2 plus bar Ni minus E naught Zn2 plus bar Zn. Okay. So E cell value is given 0.51 volt. So we can write 0.51, that is equal to you are already determined that nickel electrode potential, that is minus 0.25 minus E naught Zn2 plus bar Zn. Okay, now E naught Zn2 plus bar Zn equal to minus 0.25 minus 0.51, that is minus 0.76. This way you can able to calculate the electrode potential of any other electrode. If you know the electrode potential of an electrode and EMF of the cell. Once again, I'll take this one. Here you have to calculate zinc electrode potential. The given the cell, that is zinc electrode coupled with nickel electrode, that time develop 0.51 potential. They are not directly given the nickel electrode potential, but they given the cell which is constructed by using nickel and standard Calomel electrode. That time it developed a potential of 0.49 volt. And they given the standard Calomel electrode potential. The standard Calomel electrode potential is 0.24 volt. And you know the standard equation, Ecell equal to cathode minus E naught and the first how to calculate the nickel electrode potential. So in the second cell, the standard Calomel electrode acts as cathode and nickel electrode acts as the anode. Substituting, you will get the nickel electrode potential. Once you get the nickel electrode potential, using that electrode potential, you can able to calculate the electrode potential of zinc electrode, provided if you know the cell potential when zinc is coupled with the nickel. The cell potential is given, that is 0.51 volt. Nickel electrode potential is minus 0.25 volt. So that the zinc electrode potential developed or observed is minus 0.76 volt. Okay. I shall move to the next one. Okay. Here, a problem is a zinc rod placed in 0.1 m zinc sulfate solution at 25 degrees Celsius. Assuming that the salt is dissociated to the extent of 95%. At this dilution, calculate E naught Zn2 plus bar Zn at this temperature. Okay. See, they want to prepare an electrode using zinc rod and zinc sulfate solution. They take a zinc rod and that is dipped in a zinc sulfate solution, assuming that the concentration of that zinc sulfate is 0.1 m. But when they took a zinc sulfate and it is dissolved with a known quantity of solvent, that time the dissociation, they mixed that salt mixed with the during preparation of solution, only 95% of the salt get mixed. Okay, assuming that the salt is dissociated to the extent of 95%, not 100%. If it is 100% dissolution takes place, dissociated, then you can able to get 0.1 m zinc sulfate solution. But here only 95% is dissociated. That means you are not preparing an electrode which contains 0.1 mole. You are finding or preparing a electrode which contains a zinc sulfate solution of 95%, dissolution of 95%. And that dilution, you have to find out that dilution, you have to find out the electrode potential. Here, one more thing is given, that is E naught Zn2 plus bar Zn is given, that is minus 0.76 volt. Okay. Now, here, our intention is to prepare a 0.m solution. So that is concentration of Zn SO4 is 0.1 m. That is our intention. But how much percentage is dissociated? Percentage of dissociation of zinc sulfate is only 95%. Therefore, you have to find out actual concentration of ZnSO4 in solution. How you find out? For if it is 100% dissolution take place, you can get 0.1. But here only 95% takes place. How much concentration you have to find? So 0.1 into 95 divided by 100. The concentration of actual concentration of the solution is not 0.1. It is 0.095. Yeah. At this dilution, at this temperature, 25 degrees, you have to calculate E electrode potential. And you can use the Nernst equation, E equal to E naught plus 0.0592 by N log concentration of Mn plus. Okay. So E naught is minus 0.76 plus 0.0592. Number of electron transfer is 2. Log concentration of 0.095. Okay. Say after substitution, okay, you will get this way. Then final answer, you can observe E Zn2 plus bar Zn becomes equal to how much? So it's direct calculation. Okay, we'll get minus 0.79 minus 0.7906. This is a final. That is minus 0.7906. This is a you study the calculation of electrode potential. Now I shall consider how to calculate electrolyte concentration if you know the electrode potential of the electrode and the cell potential. Okay. Now the problem deals with the calculation of electrolyte concentration. Okay. Here the problem. So what is the concentration of nickel ion in the cell at it should be 25 degrees Celsius. It is 25 degrees Celsius. If the EMF of the cell is Ni bar Ni2 plus Ni bar Ni2 plus double bar Cu2 plus bar Cu is 0.601 volt. Given nickel electrode potential is E0 Ni2 plus bar Ni. Okay, E0 Ni2 plus bar Ni is minus 0.25 volt and E0 Cu2 plus bar Cu is 0.34 volt. Okay. From this you can predict anode and cathode. Here the higher electrode potential is copper. So Cu for electrode now act as cathode. Cathode. Or you can predict based on the cell representation. Here right side it acts as a cathode. Okay. Now I want to detect the electrolyte concentration of nickel electrolyte. So I'll take this one. Ecell equal to E0 cell. Okay, Ecell equal to E0 cell plus 0.0592 by N log concentration of reduction species by concentration of relation species. Now, you know the Ecell, or I can put what are the component given. So Ecell equal to E0 cell plus 0.0592. Number of electron transfer is here. How many electron transfer take place? 2. Okay. Log. Which one is the reduction species? Copper. So this reduction species is Cu2 plus divided by Ni2 plus. Okay. Now the EMF of the cell is given 0.601 equal to. Okay, you have to calculate E0 cell, E right electrode, cathode electrode potential 0.34 minus of minus 0.25. Okay. This becomes E cell plus 0.0592 divided by 2 log of what is the concentration of cupric ion? The given 0.75. Instead of writing this nickel Ni2, I'll take it as A. Okay, divided by A. That is A is equal to the concentration of Ni2 plus. Okay. Now I can calculate this one. So 0.601 equal to how much it becomes? It is 0.59, okay, plus 0.0296, 0.75 by 8. Okay. Now 0.601 minus 0.59 equal to 0.0296 by 0.75 by 8. 0.601 minus 0.59. So it becomes 0.011. Yeah, equal to, according to that I'll calculate, equal to 0.0296 log 0.75 by A. Okay. Now 0.011 by 0.0296 equal to log of 0.75 by A. Okay. This becomes 0.3716, 0.3762 equal to log 0.75 by A. Is it right? 0.75 by A and log 0.3167. How much it is anti-log of this? Anyone?
2.3529.
How much? 0.23529. Yeah, 0.23529. So therefore, A becomes equal to 0.75 divided by 0.23529. So the nickel ion concentration 0.03188. Yeah. Okay, this is the final. Take the problems on single electrode potential and cell potential. Okay. Yeah. This problem is similar to the previous discussed problem. Only the change in concentration is observed. Anyway, I'll take it this one once again. Here, a electrochemical cell is formed by consisting of a magnesium electrode, which is dipped that metal is dipped in a 0.042 m magnesium nitrate solution, and silver electrode in 0.35 m AgNO3 solution. So standard SEP means standard electrode potential of magnesium and zinc are minus 2.363 volt and 0.8 volt respectively. Represent the cell, write the cell reaction and calculate the EMF of the cell. You already know how we represent this cell. So while representing the cell, first you predict which electrode acts as anode and which one as cathode. Here, the silver electrode possesses a higher electrode potentials. See, Ag1 electrode that possesses a higher, that is 0.8 volt, whereas this minus 2.363. So silver electrode, that is Ag electrode, now act as cathode. It possesses a higher electrode potential than Mg electrode. Yeah. So that's why silver electrode acts as anode. And now I consider the cell representation. How we represent the cell? So first you have to write a anode Mg bar Mg 2 plus. What is the electrolyte concentration of Mg? That is 0.042 m. The two electrodes separated by means of a salt bridge. Then cathode is Ag plus, with the electrolyte concentration is 0.35 m bar Ag. Now I can write the reaction. At anode, half cell reaction, anode Mg giving rise to Mg2 plus 2 electrons. So at cathode, that is Ag plus, that it takes only one electron at a time. So we write it as a Ag plus electron giving rise to Ag, simultaneous process. So that's why the second equation should be multiplied by 2. Now the cell reaction becomes Mg plus 2Ag plus in raised to Mg2 plus Ag. These are the second part, that is representation of a cell, cell reactions and half cell reaction. Now you have to calculate the EMF of the cell. Okay, to calculate the EMF of the cell, you have to take a Nernst equation, and you know the Nernst equation, how we represent Ecell equal to E naught cell, yeah, plus 0.592 by n log concentration of reduction species by the concentration of oxidation species. And E naught cell, how we calculate? That is using the two electrodes. Silver electrode potential is 0.8, okay, minus of this one magnesium electrode, that potential is minus 2.363. I'll take the same one, minus 2.363 plus 0.0592 by number of electron transfer is 2, okay, then log reduction species concentration is silver ion concentration is 0.35, but while writing it should be the power, okay, because 2 electron transfer is observed, divided by magnesium ion concentration 0.042. Okay, now here 3.163 plus 0.0592 by 2. I'll take it as a 2 log. Okay, 2 log 0.35 divided by 0.042. Okay, so that is equal to 3.163 plus 0.0592 and log of 8.50. What is the difference? The final answer before the step 163 plus 0.0592 into log of 8.3, we get 0.9206. So Ecell becomes equal to 3.2175 volt. Okay, this is the final answer that we get. So Nernst equation we introduce, Ecell equal to E naught cell plus 0.0592 by n log reduction species by oxidation species. E naught cell is E right minus E left. Right electrode is the silver electrode, so 0.8 minus of minus 2.6363 plus 0.0592 by 2 log concentration of the silver ion, that is 0.35 to the power 2, because the reaction involves the transfer of 2 electrons. Then the final answer what we get is, after substitutions, we will get Ecell equal to 3.2175. Okay. Now I'll take the next problem. Okay. Here, calculate the E naught cupricus, that is E naught copper electrode, Cu2 plus bar Cu. What the given? Given is E Cu2 plus bar Cu, that is given 0.296 volt. Also, the cupric ion concentration is given. Okay, here it should be 2 plus. Okay, Cu2 plus ion concentration is given, that is 0.015. Yeah. Okay. What is the difference you observe? So in before I'll take first Nernst equation I'll write. This is for a single electrode potential. You have to calculate the electrode potential at this dilution. So I'll take E equal to E naught, okay, plus 0.0592. They are not mentioned the temperature, so I'll take it at 25 degrees Celsius log concentration of Mn plus. Here the given E electrode potential, okay, the given electrode potential, and you have to calculate standard electrode potential of the electrode. Okay, Now, I'll substitute this one Cu2 plus bar Cu, that is equal to E naught Cu2 plus bar Cu plus 0.0592. Number of electron transfer is here written 2. So 2 electron transfer log concentration of Cu2 plus. So I'll substitute, and the given thing is Cu2 plus bar Cu is given 0.296, that is equal to E naught Cu2 plus bar Cu plus 0.0296 a log of 0.015. Okay. See, and here you can write E naught Cu2 plus bar Cu equal to 0.296. Yeah, 0.296 minus 0.0296 log of 0.015. 0.01. 0.015. Final answer E naught plus bar Cu becomes equal to, after substitutions calculation, you will get 34984. A cell is formed by dipping zinc rod in 0.01 m zinc sulfate or a Zn2 plus solution, and nickel rod in 0.5 m Ni2 plus solution. The standard electrode potential of zinc and nickel are minus 0.76 and minus 0.25 volt respectively. Write the cell representation, cell reaction, and calculate the EMF of the cell. Okay. Here, similar to this problem is similar to the first one. Okay. Here, they given the two electrode potential. First, you predict which electrode acts as anode and cathode. Both possess a negative potential, like minus 0.076 and minus 0.25 volt. So now you find among the two electrodes, which electrode possesses a higher reduction potential. Yeah, minus 7.5 or minus 2.5. Which one is a higher electrode potential? In this negative scale, this is a minus 0.25 near to 0 positive, and this is a minus 0.76. Yeah, that means here near to positive means this is a highest that the electrode potential is high. Yeah, nickel possesses a higher electrode potential, whereas the other zinc possesses a less electrode. Nickel now electrode, that you know why it acts as an anode, electrode. Sorry, why it acts as cathode, as possesses a higher reduction potential. Here, that's why it is taken as cathode. Once you know the electrode, cathode, and anode, you can able to represent the cell. Okay. Representation. First, you write anode, that is Zn bar Zn2 plus. They given the concentration, so I'll mention 0.01. Double bar, then Ni2 plus. Concentration is 0.5 m. Then anode reaction at anode, that is familiar one, zinc giving rise to 2 electron converted into zinc ion. At cathode, nickel takes 2 electron. Net cell reaction, Zn plus. Now is it clear? Zn plus, Ni2 plus, giving rise to Zn2 plus plus Ni. Okay. This is a net cell reaction. Clear? This is a net cell reaction. Now, the next one thing is you have to calculate EMF of the cell. Am I audible? Can you confirm? My slide is visible. My voice, is it clear?
Yes, ma'am.
Yes, ma'am.
Hmm?
Yes, ma'am.
Next, you have to calculate EMF of the cell. Use Nernst equation. Ecell equal to E naught the cell plus 0.0592 by N of concentration of reduction species by the concentration of oxidation species. Is E naught cell we can calculate using the two electrode potential minus 0.76, okay, plus 0.0592 by 2 of 0.5 by 0.51 plus 0.0, or I can write directly 5.3. This terms comes to the total comes 0.0503. So E cell is 0.5603. In this way, we can able to calculate the cell potential of the cell. Now, I'll take little different types of problem. Next, I'll go into a different type of problem. Okay. So, in this problem, you have to calculate the zinc electrode potential. For that, they given the EMF of the cell. Two cell they construct. Their EMF is given. The one cell is constructed using zinc electrode and nickel electrode. Their potential developed is 0.51 volt, and the cell which is constructed using nickel and standard Calomel electrode, their potential is 0.49 volt. The question is you have to calculate zinc electrode potential. Like calculate zinc electrode potential E naught Zn2 plus bar Zn. That means zinc electrode potential. If the EMF of this cell, that is zinc coupled with a nickel electrode, which develop 0.5 volt, and nickel if coupled with a standard Calomel electrode, the potential developed is 0.49 volt. The given thing is the standard Calomel electrode potential is 0.24 volt. Okay. They are not directly given the nickel electrode potential. Okay. In the first phase, you can observe. If you know the nickel electrode potential, then only you can able to calculate zinc electrode potential using a standard equation, that is E cell equal to E naught cathode minus E naught anode. By using this equation, you can able to calculate the either cathode electrode potential or anode electrode potential or a cell potential. Okay, the two terms you should know. Here you have to calculate nickel electrode potential provided if you know the zinc electrode. Sorry, you have to calculate zinc electrode potential provided if you know the nickel electrode potential. But to calculate nickel electrode potential, they given one more cell that develops a potential of 0.49 volt. That cell is constructed using nickel and standard Calomel electrode. From this cell, you can able to calculate nickel electrode potential. Okay, the first step is to calculate E. Okay, I'll take a standard electrode potential, that one E Ni2 plus bar Ni. Okay, how to calculate this one? Standard electrode potential of nickel electrode, and you know the equation cathode minus anode, so we can write E cell equal to cathode is E naught. In this cell, the cathode is standard Calomel electrode minus E naught Ni2 plus bar Ni. And you know the standard Calomel electrode potential 0.24 minus E naught Ni2 plus bar Ni equal to E cell, that is 0.49. Okay, 0.49. Now E naught Ni2 plus bar Ni becomes equal to 0.24 minus 0.49, that is equal to minus 0.25 volt. Now, you know the nickel electrode potential. You know the EMF of this cell, okay? You know the EMF of this cell, that is 0.51 volt, and nickel electrode potential. You can able to calculate, now you can able to calculate zinc electrode potential. The next step is to calculate E naught Zn2 plus bar Zn. Okay, now we calculate that we take a cell, this one E cell. Now E cell equal to the, find out the anode electrode and cathode. Cathode is nickel, yeah. E naught Ni2 plus bar Ni minus E naught Zn2 plus bar Zn. Okay. So E cell value is given 0.51 volt. So we can write 0.51, that is equal to, you are already determined that nickel electrode potential, that is minus 0.25 minus E naught Zn2 plus bar Zn. Okay. Now E naught Zn2 plus bar Zn equal to minus 0.25 minus 0.51, that is minus 0.76. This way you can able to calculate the electrode potential of any other electrode. If you know the electrode potential of one electrode and EMF of the cell. Once again, I'll take this one. Here you have to calculate zinc electrode potential. The given the cell, that is zinc electrode coupled with nickel electrode, that time develop 0.51 potential. They are not directly given the nickel electrode potential, but they given the cell which is constructed by using nickel and standard Calomel electrode. That time it developed a potential of 0.49 volt. And they given the standard Calomel electrode potential. The standard Calomel electrode potential is 0.24 volt. And you know the standard equation, Ecell equal to cathode minus E naught and the first how to calculate the nickel electrode potential. So in the second cell, the standard Calomel electrode acts as cathode and nickel electrode acts as an anode. Substituting, you will get the nickel electrode potential. Once you get the nickel electrode potential, using that electrode potential, you can able to calculate the electrode potential of zinc electrode, provided if you know the cell potential when zinc is coupled with the nickel. The cell potential is given, that is 0.51 volt. Nickel electrode potential is minus 0.25 volt. So that the zinc electrode potential developed or observed is minus 0.76 volt. Okay. I shall move to the next one. Okay. Here a problem is a zinc rod placed in 0.1 m zinc sulfate solution at 25 degrees Celsius. Assuming that the salt is dissociated to the extent of 95%. At this dilution, calculate E naught Zn2 plus bar Zn at this temperature. Okay. See, they want to prepare an electrode using zinc rod and zinc sulfate solution. They take a zinc rod and that is dipped in a zinc sulfate solution, assuming that the concentration of that zinc sulfate is 0.1 m. But when they dissolve, when they took a zinc sulfate and it is dissolved with a known quantity of solvent, that time the dissociation, they mix that salt mixed with the during preparation of solution, only 95% of the salt get mixed. Okay, assuming that the salt is dissociated to the extent of 95%, not 100%. If it is 100% dissolution takes place, dissociated, then you can able to get 0.1 m zinc sulfate solution. But here only 95% is dissociated. That means you are not preparing a electrode which contains 0.1 mole. You are finding or preparing a electrode which contains a zinc sulfate solution of 95%, dissolution of 95%. And that dilution, you have to find out that dilution, you have to find out the electrode potential. Here, one more thing is given, that is E naught Zn2 plus bar Zn is given, that is minus 0.76 volt. Okay. Now, here, the actual, our intention is to prepare a point M solution. So that is concentration of Zn-SO4 is 0.1 m. That is our intention. But how much percentage is dissociated? Percentage of dissociation of zinc sulfate is only 95%. Therefore, you have to find out actual concentration of Zn-SO4 and solution. How you find out? For if it is 100% dissolution take place, you can get 0.1. But here only 95% takes place. How much concentration you have to find? So 0.1 into 95 divided by 100. The concentration of actual concentration of the solution is not 0.1. It is 0.095. Yeah. At this dilution, at this temperature, 25 degrees, you have to calculate the electrode potential. And you can use the Nernst equation, E equal to E naught plus 0.0592 by N log concentration of Mn plus. Okay. So E naught is minus 0.76 plus 0.0592. Number of electron transfer is 2, log concentration of 0.095. Okay. Say after substitution, okay, you will get this way. Then final answer, you can observe E Zn2 plus bar Zn becomes equal to how much? So it is direct calculation. Okay, you will get minus 0.79 minus 0.7906. This is the final, that is minus 0.7906. This is a, you study the calculation of electrode potential. Now I shall consider how to calculate electrolyte concentration if you know the electrode potential of the electrode and the cell potential. Okay. Now the problem deals with the calculation of electrolyte concentration. Okay. Here the problem. So what is the concentration of nickel ion in the cell atom? It should be 25 degrees Celsius. It is 25 degrees Celsius. If the EMF of the cell is Ni bar Ni2 plus Ni bar Ni2 plus double bar Cu2 plus bar Cu is 0.601 volt. Given nickel electrode potential is E naught Ni2 plus bar Ni. Okay, E naught Ni2 plus bar Ni is minus 0.25 volt and E naught Cu2 plus bar Cu is 0.34 volt. Okay. From this you can predict anode and cathode. Here the higher electrode potential is copper. So Cu for electrode now act as cathode. Electrode act as cathode, or you can predict based on the cell representation. Here, right side, it acts as a cathode. Okay. Now I want to detect the electrolyte concentration of nickel electrolyte. So I'll take this one. Ecell equal to Anode cell. Okay, Ecell equal to Anode cell plus 0.0592 by N log concentration of reduction species by concentration of relation species. Now, you know the E cell, or I can put what are the component E1. So E cell equal to E0 cell plus 0.0592. Number of electron transfer is here. How many electron transfer take place? 2. Okay. Log. Which one is the reduction species? Copper. So this reduction species is Cu2 plus divided by Ni2 plus. Okay. Now the EMF of the cell is given 0.601 equal to, okay, you have to calculate E0 cell, E right electrode, cathode electrode potential 0.34 minus 0.25. Okay. This becomes E cell done plus 0.0592 divided by 2 log of, what is the concentration of cupric ion? The given 0.75. Instead of writing this nickel Ni2, I'll take it as A, okay, divided by A. That is, A is equal to the concentration of Ni2 plus. Okay. Now, I can calculate this one. So, 0.601 equal to, how much it becomes? It is 0.59, okay, plus 0.0296, 0.75 by 8. Okay. Now, 0.601 minus 0.59 equal to 0.0296 by, sorry, 0.75 by 8. 0.601 minus 0.59. So it becomes 0.011. Yeah, equal to, according to that, I'll calculate, equal to 0.0296 log 0.75 by A. Okay. Now 0.011 by 0.0296 equal to log of 0.75 by A. Okay. This becomes 0.3716, 0.3762 equal to log 0.75 by A. Is it right? 0.75 by A and log 0.3762. How much it is anti-log of this? Anyone?
2.359.
How much? 0.23529. Yeah, 0.23529. So therefore, A becomes equal to 0.75 divided by 0.23529. So the nickel ion concentration 0.03188. Yeah. Okay, this is the final. And cover types of electrochemical cell. That is in brief. What are the kinds of electrochemical cell, and in particularly the detail of concentration cell. Okay. In electrochemical cell, we broadly classified into three categories. That is a primary cell, secondary cell, and the third type of cell is a concentration cell. Here, the basic difference, I'll take the primary and the secondary cell, is the reaction that involved during the process. In both the case, we observe a spontaneous redox reaction, but in the case of primary cell, the reactions is not reversible, whereas in the case of secondary cell, the reaction is reversible. Okay. Whereas the third type of cell, that is a concentration cell, that is entirely different type. Okay. There are three category under types: primary, primary cell, and second category is a secondary cell, and the third category is concentration cell. Okay, primary, secondary, and concentration cell is a special type of electrochemical cell in which reaction cannot be reversed. In the case of primary cell, reactions reactions cannot be reversed. Okay. Reactions cannot be reversed. Okay, it cannot be reversed. Like it only acts as a galvanic cell. It will not act as a electron. That means chemical energy is continuously changed into electrical energy. In case of primary cell, anode is a negative electrode and cathode is a positive electrode. Okay, this cannot be reversed. Okay, in the case of primary cell, the anode is always the negative electrode and the cathode positive electrode. The cell can be discharged but not recharged. Here it only we observe discharge reaction. It can be discharged but cannot be recharged. Okay, recharging is not possible. This is in particularly primary cell. Okay, and what is secondary cell? What kind of cell we considered as a secondary cell? Say like a lithium, that battery also comes under a cell only. Lithium cell, they are considered as a secondary cell. Then there mainly the cell reaction can be recharged. In almost all rechargeable battery comes under secondary cell. Okay, in which the chemical reactions are reversible. Secondary cell means here chemical reactions are reversible. It can be reversible. That means here the cell is being charged. The next thing is a cell can be charged. A cell is being charged. Okay, these are the few points under secondary cells. Okay, then here the anode becomes a positive electrode and the cathode is a negative electrode during charging. Okay, clear? During discharging time, when the discharge reaction take place, discharge reaction means there is a conversion of chemical energy to electrical energy. Okay, so when the cell act as a secondary cell, that time during discharging time it act as a galvanic cell. So anode is negative electrode and the cathode becomes a positive electrode. During charging time, the cell reaction gets reversed. That means charging means electrical energy is stored in the form of chemical energy. Okay, it is stored in the form of chemical energy. That time anode becomes positive electrode and cathode is a negative electrode. That means during charging time, it acts as a electrolytic cell. Okay, so in the secondary cell, during charging time, it acts as an electrolytic cell. During discharging time, it acts as a galvanic cell. Okay, so this is a basic difference or the changes what we observe between primary and secondary cells. Okay, in the case of primary cells, the reaction cannot be reversed. So if you take primary cell with that of secondary cell, here the primary cell reaction cannot be reversed. Okay, the first, whereas here reactions are reversible. Reactions are reversible. I'll just mention the things. Okay, and the thing is here it only acts as a galvanic cell, whereas here it acts as a galvanic cell as well as a electrolytic cell. And here electrical energy is stored in the form of chemical as well as a chemical energy is stored in the form of electrical energy. But in the case of primary cell, only discharge reaction is possible. Okay, it's about the primary and the secondary cell. Okay, category of cell, what we called it as a concentration cell. So here we mainly concentrate on in the syllabus. We can observe this. Okay, see, I'll take one example like Zn bar Zn2 plus double bar Zn, sorry, Cu2 plus bar Cu. Okay, here I'll mention the concentration. Here it is 0.5 m and here I'll take 1 m. Okay, and I'll write one more cell, that is 1 m double bar Ag plus 0.1 m bar Ag. Okay, I wrote two cells, one zinc coupled with the copper, cell silver coupled with the another silver electrode. Okay, what is the basic difference you observed? Zn, Zn2 plus, now you can find. Okay, same double bar Zn2 plus 0.1 m. Okay, bar Zn. Okay, now what is the difference you observed with the first with that of the third one? Okay, what is the difference? Is it same? In the first cell that is constructed using different electrode. Yeah, one is a zinc electrode, another one is a copper electrode in the first cell. In the second cell, both electrodes are made up of silver. Okay, both electrodes are made up of silver. And even third also what we observed, both electrodes are made up of zinc electrode. Okay, here we use the same electrode. In the second case, we use the same electrode. If you use a same electrode, is this possible to get a potential? EMF equal to E naught right minus E naught left. If you take, you will get any potential. See, you know, zinc electrode potential minus 0.76 minus of minus 0.76 it becomes. So the net value is a 0. So there is no potential. So in order to generate a potential, if you take a same electrode, okay, then it's not possible. In order to generate a potential, I'll just vary the electrolyte concentration, provided I'll take the same electrode. Okay, I'll take same electrode, only I'll change the electrolyte concentration. See, if electrolyte concentration is the same, then I'll get the same potential. Yeah, both right electrode and left electrode potential is same. If I take a different electrolyte concentration, then I'll get a potential, or EMF of the cell is observed. And that type of cell, what we called it as a concentration cell. That is an electrochemical cell. Okay, concentration cell is considered as a electrochemical cell. Okay, how it is formed? Formed by the combination of, what you observed, same thing, that is same electrodes, is it? Same electrodes dipped in the same electrode, dipped in the what electrolyte? It is same again, dipped in the same electrolyte solution. What you observe the difference? Same electrolyte solution of different concentration. Yeah, the difference is only the concentration. Different in different concentration. And that cell, what we called it as a concentration cell. Clear? It's called as concentration cell. Clear? An electrochemical cell formed by the combination of same electrode, silver electrode and silver electrode, same electrode, dipped in a same electrolyte solution. In both the case, we use silver ion. But there is a difference in the electrolyte concentration. There is a difference in the electrolyte concentration. Good example, I already written AgNO3. If you want, I can write it here. The construction part, I'll take Ag bar, we'll write like this, AgNO3 with a concentration 0.01 m double bar Ag 0.1 m bar Ag. This is an example for concentration cell. So if I want to construct this cell, I'll take a silver metal that is dipped in a silver nitrate solution. Okay, this is a silver Ag dipped in Ag. Another metal I'll take, electrode. Again, that is also dipped in a same electrolyte solution, AgNO3 solution. Okay, and these two electrodes are connected by means of voltmeter, and the electrolyte is connected by means of a salt bridge. Connected by means of a salt bridge. This one is also considered as a salt bridge. Okay, this is both Ag. This is AgNO3. What is the difference you observe? This is 0.1 m, whereas this one AgNO3, this is 0.01 m. In general, I'll take this one is a C1 and this is C2. Okay. So now I'll write the half cell reaction. What type of half cell reaction is observed? Okay. At anode, oxidation reaction takes place. That is Ag giving rise to Ag plus plus electron. The cathode electrode also a silver electrode, and the ions which observed in the cathode is a silver ion. It takes electron forming Ag. And what do you observe? Ag giving rise to Ag plus. What is the Ag plus ion concentration here? I'll mention here 0.01 m. Okay. Because I should recognize which ion. Here at the anode, you observe Ag plus ion with the concentration 0.01, whereas at cathode, you observe 0.1 m. Okay, what is the next reaction? So it is just observed like the transfer of metal ion from an electrode of higher electrolyte concentration to an electrode of lower electrolyte concentration. But actually, it takes place through electrochemical reaction. Yeah, it is not a simultaneous or it is not just a transfer of metal ion, but it is a transfer of electron. Okay, the reaction takes place through a spontaneous redox reaction. Okay, here if you observe the final equation, you can observe like it is just a transfer of metal ion from a higher electrolyte concentration to a lower electrolyte concentration. But actually, if you observe the cell reaction, it takes place through a electrochemical reaction, transfer of metal ion from an electrode of higher electrolyte concentration to an electrode of lower electrolyte concentration. Okay, this is a reaction what you observe in a concentration cell. Now I'll derive a Nernst equation in particularly for a concentration, in particular a concentration for a concentration cell. Okay. First I'll write a Nernst equation for half cell. Okay, Nernst equation for half cell. I'll take this one, E left. How we write? E naught left electrode plus 0.0591, or I'll take 2.303. Okay. Take 2 point. I'll take 2.303 RT by NF log concentration of what is the left electrode concentration? Generally, we'll take C1. Here I'll write the C1. I'll take same concentration is C1. Okay. Same way I'll write E right equal to E naught right electrode plus 2.303 RT by NF log concentration of C2. Okay. I know the left electrode potential and the right electrode potential. Once you know the electrode potential, you can able to calculate the cell potential. Okay. So that is Ecell equal to E right electrode potential minus E left electrode potential. And you know the right electrode potential is E naught R plus 2.303 RT by NF log, I'll simply take C2, okay, minus of EL plus 2.303 RT by NF log C1. Okay. Here ER minus E naught R minus E naught L get cancelled because both we use the same electrode. Say if we consider a silver electrode, AG plus AG, AG bar plus AG, AG bar, AG plus double bar, AG plus bar, AG with a concentration like C1, C2. Okay, same electrode. So that's why the electrode potential is same. Both the case, the electrode potential is same. Only remaining thing is 2.303 RT by NF log C2 minus 2.303 RT by NF log C1. So I'll take this way, 2.303 RT by NF log C2 minus log C1. Okay. So in this place, we can write this way, 2.303 RT by NF, okay, RT by NF log C2 by C1, log A minus log B. We can write it as log A minus B. Okay. See, this is a Nernst equation for a cell potential. Okay. For particularly if the electrolyte concentration is different with the same electrode. Okay. Using the same electrode. Clear? So you can represent this one at 25 degrees Celsius. At 25 degrees Celsius, you know, the all things are equal to 8.314, F is 96,500. So we'll get Ecell equal to 0.0592 by N log C2 by C1. Okay, and here you can get a potential or E cell positive. Okay, E cell can be positive when it can be positive. It can be positive only if this is a one condition, C2 is greater than C1. Okay, it should be the C2 is greater than C1. So that's why while constructing a concentration cell, okay, in the concentration cell, the electrode with lower lower electrolyte, not electrode, lower electrolyte concentration. This is a condition. Concentration act as anode. Okay. Lower electrolyte concentration act as anode. Okay. And that of electrode with higher electrolyte concentration, electrode act as cathode. Okay, while choosing the, say I'll give the two electrode like Ag, each time I'll take the same one, Ag bar Ag plus with the 0.2 m, and the other electrode Ag bar Ag plus with the 0.1 m. You choose which one acts as anode and cathode. The one which possesses a higher electrode potential, electrolyte concentration act as a cathode. Here the electrolyte higher concentration is this one. This should act as cathode, and this one anode. And while representing, you will take this way, Ag bar Ag plus. Here you have to write 0.1 m double bar same Ag bar Ag plus 0.2, like. Okay, see here while constructing the concentration cell, the electrode with the higher electrolyte concentration act as cathode. Okay. Once again I'll take, okay, here the concentration cell, an electrochemical cell formed by the combination of same electrodes dipped in the same electrolyte solution of different concentration. A good example is like a silver metal is dipped in a silver ion solution with a concentration 0.1 m, which is coupled with another silver electrode with the electrolyte concentration 0.1 m. Okay. The example like Ag bar AgNO3 with a concentration 0.01 m double bar Ag into the 0.1 m concentration bar, double bar here, it should be AgNO3, okay, or else I can write it Ag plus NO3 bar Ag, okay. Here at the 0.1 m concentration right side and 0.01 m concentration left side, because while constructing the concentration cell, the electrode with the higher electrolyte concentration electrode should be kept right side, or it should act as a cathode. Then only we can get a positive EMF. Okay. And the next thing is the construction part. The silver metal dipped in a silver nitrate solution, general concentration aluminate C1, and the other electrode, the same metal dipped in a C2 concentration. The cell reaction, what we observed is at anode, oxidation reaction take place, Ag giving rise to Ag plus electron, and here I have to mention the concentration of that electrolyte solution, and at cathode, Ag plus electron giving Ag. What is the net reaction? It is just a transfer of metal ion from an electrode of higher electrolyte concentration to an electrode of lower electrolyte concentration. It appears like just a transfer of metal ion from one electrode to another electrode, but it actually takes place through electrochemical reaction. Now, the Nernst equation can be represented, Nernst equation for a half cell. So E left equal to E naught left plus 2.3 RT by NF log C1. For right electrode, the same thing, E naught plus 2.303 RT by NF log C2. And E cell is a nothing but E right minus E left. So we can finally we can arrive the Nernst equation for a concentration cell, that is E RT by NF log C2 by C1 at the 25 degrees Celsius. So the representations equation becomes E cell equal to 0.0592 by N log C2 by C1. So E cell can be positive only if C2 is greater than C1. In the concentration cell, the electrode with the lower electrolyte concentration act as anode, and that of electrode with the higher electrolyte concentration act as cathode. So then only we'll get a positive EMF. Otherwise, the EMF becomes 0 or a negative. A few along with this, you have to study few problems that is related to Nernst equation. I'll write the problem because I'm not type 2. That is calculate EMF of the concentration cell, EMF of the concentration cell. They given the concentration cell like this, Cu bar, Cu2 plus 0.072 m double bar Cu2 plus 0.32 m bar Cu. Okay. Along with this, they ask write the cell reaction. Write the half cell and net cell reaction. Okay, write the half cell and net cell reaction. You have to calculate the EMF of the cell. Along with this, you have to find a half cell and net cell reaction. First, I'll write the cell reactions. Okay, at anode, you know, oxidation. Which one is a metal? That is a Cu, giving rise to Cu2 plus 2 electron. What is the electrolyte concentration? That is 0.072 here, M. Okay. Then at cathode, Cu2 plus the concentration 0.32 m plus 2 number of electron, giving rise to Cu. What is the net reaction? That is Cu2 plus 0.32 m, giving rise to Cu2 plus 0.072 m. Okay. Then next thing is you have to calculate EMF of the cell. Okay. And you know the Nernst equation for concentration cell. E cell equal, they are not mentioned the temperature, so that's why I'll take it for at 25 degrees Celsius. 0.0592 by N log C2 by C1. Okay. Log C2 by C1. I'll substitute the values. So E cell equal to 0.0592 by N log C1. C1 means the higher electrolyte concentration, that is I'm sorry, in the question it is 0.032, not 32. Okay, 0.032. Here also 0.032. 0.032 divided by 0.072. Okay. And final answer here, N is, I'll represent N equal to 2. Okay. So final answer E cell, you will get 0.0, if after calculation you will get 0.0726 volt, I think. Take the next one. Next problem I'll write. A concentration cell constructed by dipping two copper electrodes in 0.001 m and 0.1 m TuSO4 solution. Okay, TuSO4 solution, and the two solution and the two solutions are connected by salt bridge, connected by means of a salt bridge. Calculate the EMF of the cell at 298 Kelvin. Write the cell representation and cell reaction. Okay, this is a question problem. First, you have to write the cell representation. You know what is the electrode present here? Both are copper electrodes. So Cu bar CuSO4 double bar CuSO4 bar Cu. Now you mention the concentration. There are two concentration. The one is 0.001 m, and one is a 0.1 m. Okay, which one is higher? 0.1 m is higher. See, you know the 0.1 m greater than 0.001. So it acts as cathode, and this is act as anode electrolyte. So you can mention 0.001 m here, and here you write 0.1 m. This is a representation of the cell. Now I'll write the half cell reaction at anode. Cu giving rise to Cu2 plus 0.001 m plus 2 electron. At cathode, what is the cell? That is electrolyte Cu2 plus with the concentration 0.1 giving rise to Cu. Here it takes 2 electrons. So what is the net cell reaction? That is Cu2 plus 0.1 m giving rise to Cu2 plus with concentration 0.001. The next step you have to calculate Ecell equal to 0.0592 by n log C2 by C1. Okay, and you know the values, that is 0.0592 by 2 log 0.1 by 0.001. So 0.0296 and then log 100. Okay, that is to get cancelled. So 0.096 log, I'll put 100. Okay, that is equal to 0.0592. This is the final answer what we observed in this case. Okay, E cell equal to this much. Concentration cell was constructed by immersing 2 kg electrode of 0.01 m and 10 m AgNO3 solution. Okay. Then question, write the cell representation, cell reaction, and calculate the EMF of the cell. Okay. First, I'll write representation, and you know, higher electrolyte concentration act as cathode, Ag plus 0.01 m double bar Ag plus here 10 m bar Ag. Anode giving electron Ag giving rise to Ag plus 0.01 m plus electron at cathode Ag plus electron giving rise to Ag, and here it is 10 m. What is the net reaction? Ag plus ion with the higher electrolyte concentration to move to a lower electrolyte concentration. Next thing is how to calculate the cell. Ecell equal to 0.0592 divided by 2 log C2 by C1, 0.0592 by 1 log 10 by 0.00, okay, 1, no, only 1, 0, 1, okay. So final answer is cell equal to 10 by 0.001, 1 point, we'll get to 1.7, sorry, 0.1773 volt. This is the final answer. Okay. Next, I'll take one more problem, but I'll write the problem. Okay, you possible you can solve this one. Concentration. A concentration cell. Okay. Concentration cell was constructed by same, only concentration is different, immersing 2 Ag electrode in 0.05 m and 0.1 m AgNO3 solution. Write same thing, write cell representation of cell reaction and calculate the EMF of the cell. Okay. Representation and the reaction is the same. The cell calculation is just, you have to mention the concentration corresponding to this problem, like your 0.0592, sorry, here it is n and this is 1 log point, which one is higher, 0.05 m or 0.1? The higher is 0.1 divided by 0.05. So we will get Ecell value equal to 0.12 volt. This is today we shall take types of electrodes. Today's topic that deals with the types of electrodes. Mainly there are 6 types of electrodes are observed. Okay, 6 types of electrodes. Okay, there are total 6 types of electrodes are observed. Okay, the first category of this electrode you already studied one, that is what we call it as metal ion electrodes. Okay, metal ion electrodes. I put one diagram here. So here, this is a one metal, say M metal, and this metal, it should be dipped in a Mn plus solution. Okay, a metal M is dipped in a solution Mn plus. Okay, and that type of electrodes are called it as a metal ion electrode. That is nothing but an electrode. That means that an electrode this type, and write it like here, this type consists of a metal, dipped in a solution containing its own ions. Okay, you take M metal, and that metal should be dipped in a solution containing its own ion, like Mn plus ions. Okay, M should be dipped in a Mn plus ions. And how we represent this electrode? See, how we represent this electrode? Okay, see, this is simple. Like in case of Daniel cell, you already represented a copper electrode and zinc electrodes, etc. Okay, here the representation I'll take. Okay, take simple one. Okay, zinc electrode, zinc. Okay, that is dipped in a Zn2 plus solution, or Cu dipped in a Cu2 plus solution. Okay, so this is an example for metal ion electrode. And the reaction, electrode reaction in a metal ion electrode is zinc, okay, ion, and take a reduction reaction gives zinc, takes to electrode, may act as anode or cathode depending upon the other electrode. Okay, this you already observed in while solving a problem. Like if you take a zinc, couple zinc with the copper, so that time this electrode act as anode, yeah, and copper act as a cathode. If you couple a copper with silver, okay, Ag plus, then Ag act as cathode and silver act as anode. Depending upon the other electrode, the said electrode acts, either it may act as anode or cathode. This is the first type of electrode, metal ion electrode. An electrode consists of a metal dipped in a solution containing its own ion. Now I'll take the second type of electrode. Okay, the second type of electrode, what we call it as metal salt ion electrode. Metal salt ion electrode. It's also called as, or may express it as metal insoluble salt ion electrode. Metal insoluble salt ion electrode. Okay, metal insoluble salt ion electrode. Here, this electrode consists of a metal. Okay, consists of metal, is in contact with a solution of sparingly soluble salt of the same metal, sparingly soluble salt of the same metal, okay, containing an ion of the salt. I'll take one example, like a calomel. A good example is a calomel electrode. In the calomel electrode, a mercury is present, which is in contact with mercurous chloride. This mercurous chloride is a sparingly soluble salt. That means a metal mercury is in contact with a sparingly soluble salt of the same metal containing anion of the salt. Okay, here anion of the salt it contains. Or even the another electrode is Ag bar AgCl bar Cl minus. Okay, silver chloride electrode. Here silver chloride is a sparingly soluble salt. In the silver chloride electrode, will take a silver metal that is dipped in a AgCl solution which contain a little quantity of AgNO3, so it forms a sparingly soluble. Some precipitation are present in that mixture or in the solution or in the electrolyte, and that type of electrodes are called as a metal salt ion electrode. That is metal insoluble salt ion electrode or a metal salt ion electrode. Here a metal is in contact with a solution of a sparingly soluble salt of the same metal dipped in a solution containing anion of the salt. Here a mercury is placed at the bottom and which is in contact with a sparingly soluble mercurous chloride. In turn, it is covered with the electrolyte KCl. Okay, and to make an external electrical contact, a platinum wire is immersed, and this electrode, what we call it as a Calomel electrode, and this electrode may act as anode or cathode. So that's why this electrode also called as a reference electrode. It is called as a reference electrode. Okay, this is an example for reference electrode. Okay, even the metal ion electrode also called as a reference electrode. Even metal salt ion called as a reference. It can be used as a standard reference while measuring the electrode potential of other electrode. Okay, the second type of electrode is a metal salt ion electrode. What the basic difference between first one and second one? In the first one, we use a metal which is dipped in a metal ion solution. Here, a metal is dipped in a sparingly soluble salt of the same metal containing anion of the salt. And the third type of electrode, this you already studied in your PO. The third type of electrode, that is what we called it as a gas electrode, called as gas electrode. Okay, a gas electrode consists of, that's a good example for gas electrode is a hydrogen electrode. The hydrogen electrode is a gas electrode. So how we represent the gas electrode? The hydrogen electrode, platinum is in contact with H2 gas and in turn it contact with H plus ion. Yeah, that means here we use a gas molecule. That means you know very well. 1 atmosphere, under 1 atmosphere pressure, you introduce a hydrogen gas bubbles. On the surface of the inert metal, a gas molecule is in contact with the ions of the solution containing ions of the gas molecule, like H2 gas is in contact with the H plus ions. So, and this the variation in the phase, in turn, an electrical double layer is developed. As a result, and establishes a equilibrium between the gas molecule and the ions, and the potential is again picked up by an inert metal platinum. Okay, so in turns, the gas electrode we may considered as it consists of a gas bubbles. Gas bubbles is in contact with an inert metal wire. Where it is present, it is immersed. It is immersed in solution containing ions of the gas molecules. Ions of the gas molecules. The metal provides, which one is a metal? That is a platinum, provides an electrical contact and facilitates the establishment of equilibrium equilibrium between the gas molecule, between the gas and its ions. There exists an equilibrium between H2 and H plus ions, okay, and there is an equilibrium between these two, and again the potential is picked up by a platinum electrode. The good example for gas electrode is a hydrogen electrode, okay, and even the chlorine electrode. And you know the reaction that taking place in a hydrogen like a electrode, that is H plus ion takes electron and giving H, and two H molecules combines forming H2 gas, liberation, okay. This is a third type of electrode, called it as a gas electrode. In the gas electrode, one of the component used is a gas molecules. That's why the electrode we called it as a gas electrode. It consists of a gas molecules which is bubble on the inert surface, which make in contact with an electrolyte of the same gas molecules, okay, electrolyte of the gas molecules containing ions of the gas molecules. Like if you take another gas electrode like a chlorine electrode, there we use chlorine gas, chlorine electrode. We may observe this type of glass electrode. There platinum, over that we introduce a chlorine gas and makes a contact with the chloride ions, and the potential is picked up by an inert metal, platinum, okay. And the fourth type of electrode, what we called it as a redox electrode, or it is called as a oxidation reduction electrode, okay. Oxidation reduction electrode is a fourth type, or it is simply called as redox electrode, okay. It's a redox electrode. It's like a simple platinum wire is inserted in the electrode. A platinum wire is inserted, okay, and in a solution containing, or a solution which can able to show variable in the oxidation state. Like we may introduce a platinum is introduced, wire is introduced to a ferrous ammonium sulfate solution, and this ferrous ammonium sulfate solution contains Fe2 plus ions. To this, if you add K2Cr2O7, you know it is an oxidizing agent. FAS is a reducing agent. A redox reaction take place. This is an oxidizing agent. K2Cr2O7 is an oxidizing agent. FAS is a reducing agent. A redox reaction take place. That time Fe2 plus changes to Fe3 plus when you add Cr plus 6 ions. A redox reaction take place. Yeah, as soon as Cr plus 6 is introduced, the number of the electron is get oxidized. Fe2 plus get oxidized to Fe3 plus. At the same time, Cr plus 6 reduced to Cr3 plus. A redox reaction take place. Okay, and this change in the variable in the oxidation state, or the potential arises from the tendency of one form changes into another form, and this change in concentration of Fe2 plus with that of Fe3 plus is picked up by a platinum wire, a inert platinum wire, and it shows the change in the potential, or it shows some potential, and that potential what we called it as a redox potential. So that's why these electrodes are represented this way. A platinum wire is in contact with the ions like Fe2 plus and Fe3 plus, okay, or platinum contact with the cesium. It also shows a 3 oxidation state, cesium 4 and cesium 3, or platinum is in contact with the SN2 plus and SN4 plus, okay. So these are the different oxidation state we observed, and that's why because of the variation in the oxidation state by the addition of redox or oxidation or a reducing agent, we observe a change in the concentration. In turn, it shows some potential, and that potential is picked up by a platinum electrode, and that electrode what we called it as a redox electrode, okay. Or in other words, we can write it as an oxidation reduction electrode is one in which the electrode potential arises from the presence of or by the presence of oxidized and reduced forms of the same substance in a solution. Okay, then the potential developed is picked up by an nut electrode like platinum. Okay, so we can represent this electrode this way. Platinum is in, it's due to change in oxidation state. We can observe a potential, and this type of electrode, what we called it as a redox electrode. Here, the platinum is an inert metal. It will not undergo oxidation or reduction reaction, but the ions which present in the electrolyte, they undergo oxidation or the reduction species depending upon the other added electrolyte. So it shows a change in potential, and that potential, what we called it as a redox potential. Okay, or redox electrode, called it as a redox electrode. I'll take the fifth type of electrode. The fifth type of electrode, what we call it as amalgam electrode. Metal, even it is called it as a metal amalgam electrode or amalgam electrode. Fifth type of electrode is a metal amalgam electrode. Okay, this electrode is similar to that of metal ion electrode. It almost resembles with the metal ion electrode. How we represent metal ion electrode? Like lead is in contact with lead ion. Yeah, this is a metal ion electrode. Yeah, metal ion electrode representation. Okay, so for in the case of amalgam electrode, instead of using metal, we use metal amalgam. It is a metal is coated by means of a mercury, and that is dipped in a metal ion solution. This is an example for a metal amalgam electrode. Okay, then how we define a metal amalgam electrode or a metal amalgam? Okay, a metal amalgam is in contact with which ion? With a solution containing its own ion. Here we can get a very few type of metal amalgam electrode. That means the metal can able to hold amalgam, those electrodes, and it is stable over a temperature. Then only we can produce a metal amalgam electrode. The good example for metal amalgam electrode is a lead amalgam electrode. Here, a metal amalgam is in contact with the electrolyte solution containing its own ion. Okay, and the sixth type of electrode, what we called it as a ion selective electrode, called as ion selective electrodes, and it's also called as a membrane electrode. Also called as membrane. It's also called as membrane electrode. Metal ion selective electrode called as a membrane electrode. Okay. See, the good example for membrane electrode is glass electrode. You can observe a bulb. This is what we call it as a glass bulb, sensing bulb. This bulb can able to exchange a particular ion, or it can act as a membrane. between internal solution with that of outer solution. And this electrode usually we dip in a solution whose electrolyte concentration is to be determined. Like if you want to detect H plus ion concentration, the electrode is dipped in this. Along with this, we have to dip another electrode, like even a zinc electrode, any other type of electrode. And these two electrodes are connected by means of a salt bridge. Okay, thereby we can construct a cell and we can able to get some EMF. Based on that EMF, we can able to detect the electrolyte concentration. Okay, so here then what is ion selective electron? It is a membrane electrode. Here a membrane is in contact with the solution with which it can exchange their ions. Okay, in case of ion selective electrode, here we can write it like this: a membrane, it may be a glass membrane. Okay, a membrane is in contact with a solution. Is it? It contact with the solution. What kind of solution? With which it can exchange their ions. So this membrane can able to exchange a particular type of ion. It is a selective ion and is specific to a particular ions. Okay, a membrane is in contact with the solution with which it can exchange their ions. Here, a membrane, glass membrane, with that will take a HCl solution of particular normality. And this H plus ion interact with this H ion. So there is a development of electrical double layer. So a potential is developed. Okay, and that type of electrode, what we called it as a ion selective electrode. Particularly the glass electrode can able to exchange H plus ion. Okay, glass electrode exchange H plus ion. Now I comes to types of electrode. What we called it as a reference electrode. These electrodes can be used as a standard reference while measuring the other electrode. I already discussed 6 type of electrode. All these 6 type of electrode can be used as a reference electrode. So the reference electrodes are the electrode with reference to those the electrode potential of any other electrode can be measured. How we define? The reference electrodes are the electrode with reference to those the electrode potential with reference to those electrode, the electrode potential of any other electrode potential can be measured. That type of electrode are called as a reference electrode. Here are the reference electrode are the electrode with reference to those the electrode potential of any other electrode potential can be measured. Okay, so it can also, this reference electrode can also act as anode as well as cathode depending upon the nature of the other electrode. That means it is not a restricted, this electrode should act as anode or this electrode, ion selective electrode should act as cathode. It's not restricted. It depends upon the other electrode. Based on the other electrode potential, the reference electrode act as anode as well as a cathode. There are 2 types we classify the reference. This electrode again comes under 2 classifications: primary reference electrode and the secondary reference electrode. Primary reference electrode and secondary reference electrode. There are 2 types: primary reference electrode and the secondary reference electrode. The primary reference electrode is the one in which the electrode potential is arbitrarily fixed to 0. That is only one electrode that is Hydrogen electrode comes under primary reference electrode. All other type of electrode comes under secondary reference electrode, like metal ion, metal salt ion, ion selective electrode, redox electrode. They all comes under secondary reference electrode. So Calomel electrode, they all comes under a secondary reference electrode. This is about reference electrode. Reference electrode are the electrode with reference to those the electrode potential of any other electrode potential can be measured. Okay, the construction and working of Calomel electrode. Okay, how we construct the electrode and how it acts as anode and cathode. Okay, construction and working of this electrode. How we construct the Calomel electrode? Say the Calomel, or in generally this Calomel electrode is also called as mercury mercurous chloride electrode. Okay, it is called as mercury mercurous chloride electrode. So first I'll take the construction of this electrode. It consists of a glass vessel. You can observe it consists of a glass vessel having a bent side tube. Sometimes you may observe this type of tubes. Okay, a bent side tube. Here a bent side tube. Okay, then this is a outer appearance, that is a glass tube. It consists of a glass vessel having a bent side tube. Pure mercury is placed at the bottom of the tube, that you can observe. This is a mercury. A pure mercury is placed at the bottom of the tube. Hg is nothing but a mercury. Then, which is covered with a paste of mercury mercurous chloride. It is a paste, it is not a solid, it is a paste. Okay, a paste of mercury mercurous chloride, that is Hg2Cl2 plus Hg paste. Okay, mercury mercurous chloride paste is placed above this mercury layer. Okay, then the remaining whole portion is covered or filled by means of KCl solution. Okay, and this KCl may be normal, decinormal, or saturated. Three categories solution you can use. Okay, either you can use saturated KCl or normal KCl or decinormal KCl. Clear? Then, so a platinum wire, a simply platinum wire sealed onto a glass tube. This is a glass tube. In that we introduce a platinum wire. Okay, simply a platinum wire sealed into a glass tube is dipped in a mercury layer. Mercury is dipped in a, it should be little more, mercury layer. It's used to provide an external electrical contact. External, it provides an external electrical contact. Okay, then we use the salt, this side tube. Yeah, the bent tube or the side tube is used to make as electrical contact with the salt bridge, or make the contact with the salt bridge. This is about the construction. Here, what are the components we use? We use mercury, mercurous chloride, then KCl, and the one more thing is platinum. Okay, it consists of, let's explain again, it consists of a glass vessel. In that is having a bent tube. Okay, bottom of the glass vessel a mercury is placed. Above this mercury a paste of mercury mercurous chloride. The remaining portion is filled with decinormal, normal or saturated KCl. Okay, then a platinum wire sealed on the glass tube is inserted in the middle of the mercury layer, used to provide an external electrical contact. The side tube helps to make a contact with the salt bridge. Okay, so this is about the construction of mercury mercurous chloride electrode. Now I'll take a representation. How we represent the electrode? Okay, see, bottom layer is a mercury. That mercury is in contact with which one? Mercurous chloride, Hg2Cl2. is in turn contact with Cl. I'll use a saturated, so I'll write saturated. And what is this mercury? Mercury is a solid or a semi-solid component, so that's why I'll put yes. Okay, this is a representation of the electrode. Next, this is a reference electrode, so it acts as anode as well as a cathode. Okay, it can act as anode or it may act as a cathode depending upon the other electrode, depending on the nature of the other electrode in the cell, depending upon the nature of the other electrode in the cell. Okay, now I'll take when it acts as anode, what is the reaction take place? Okay, when or cathode, okay, when Calomel electrode acts as anode, undergo, if it acts as anode, what is the reaction possible? That should be an oxidation, undergo oxidation. Okay, oxidation. Then electrode reaction, we represent this way, electrode reaction. See here, the active metal is a mercury. Yeah, that metal should undergo oxidation. So that means the mercury undergo oxidation. So when it acts as anode, Hg undergo oxidation. Hg, here it should give mercurous ion, not mercuric ion. So I'll write this way, Hg2 plus 2 plus 2 electron. This is not mercury, this is mercury reaction. Mercury gives mercurous ion with the liberation of 2 moles of electron. But as soon as a mercurous ion is formed, it is in contact with which ion? It contact with here Cl minus ion. So that's why as soon as mercurous ion is formed, that is Hg2 plus is formed, it interact with the 2Cl minus, giving rise to Hg2Cl2. What is the actual reaction when it acts as anode? That is mercury interact with the chloride ion, forming mercurous chloride with the liberation of 2 moles of electron. Okay, this is a reaction when it acts as anode. When it acts as anode, this reaction take place. When it acts as cathode, what is a possible reaction? When it acts as cathode, it undergo reduction reaction. When it acts as cathode, it undergo reduction. Okay, it undergo reduction. Possible reaction, we can represent this way. What is the active ion? You already know, Hg2 plus ion. This takes 2 electron and forming mercury. Okay, form mercury. How this Hg2 plus ion is generated? That is by the dissociation of mercurous chloride. Dissociate to forming mercurous ion with the formation of 2 moles of Cl minus. What is a cathode reaction? Then cathode reaction is mercurous chloride takes 2 electron forming, okay, here it should be 2, otherwise it will not balance, 2 Hg plus 2Cl minus. Okay, 2 Hg plus 2Cl minus. This type of reaction take place when it acts as cathode. Okay, when it acts as anode, we observe mercury gives mercurous ion with the liberation of 2 electrons. That mercurous ion takes 2 chloride ion forming mercurous chloride, or in general the net cathode reaction is mercury interact with the chloride ion forming mercurous chloride with the liberation of 2 electrons. When it acts as a cathode, reduction reaction take place. Mercurous ion takes electron from mercury. Then mercurous ion is generated by the dissociation of mercurous chloride, forming mercury and chloride ion. So net reaction is this get cancelled. So this is get cancelled. The net reaction becomes mercurous chloride interact with the electron forming mercury and chloride. So we can write the net reversible reaction. Net reversible reaction. I'll take reduction reaction is the forward reaction. Electron or giving rise to 2Hg plus 2Cl minus. I can write corresponding to this, I can write the Nernst equation, or in other words, electrode potential of this electrode. Electrode potential, I'll represent this way, is equal to E naught minus 2.303 RT by NF log, here Cl minus to the power 2. Why I took 2? Because here Cl involved 2 electrons. So that's why I should take to the power 2. Okay, or here I know this n is 2. So I can represent this way. E is equal to E naught minus 2.303 RT by F log Cl minus. From this equation, it is indicate that electrode potential depends upon the chloride ion concentration. Okay, the electrode potential depends on the chloride ion concentration. Okay, electrode potential depends on concentration of the chloride ion. So at 298 Kelvin, if you take a different uh, uh, electrolytes, different normal electrolytes, we can get a different potential. If you take a saturated KCl in the tube, so you will get 0.2422 volt. If you take one normal KCl, you will get 0.281 volt. If you take decinormal KCl, you will get a potential of 0.334 volt. So it holds. Electrode potential depends upon the chloride ion concentrations. Okay, clear? Say if you put a different concentrated KCl solution, we'll get a different potential. But while taking it as a reference electrode, usually we use a saturated KCl as a reference electrode because it can withstand with the temperature. So even increase in a little increase in the temperature, the concentration, the increase in the temperature, it will not change the electrode potential. It's withstand with the temperature. Okay. Say the main advantage of using this electrode is advantages. One thing is it is a simple construction. Simple to construct, is it? It is simple to construct. The second thing is cell potential is reproducible. Cell potential is reproducible and stable over a long period. It is because it withstand and does not vary with the temperature. These are the main important thing we observed in this electrode. Does not vary with the temperature. Instead of using hydrogen electrode, we normally use Calomel electrode because of these advantages. Okay, it withstand with the temperature. Is simple construction, does not vary with the temperature. Okay, again I'll recollect these things. Okay, say construction and working of Calomel electrode. Here this electrode is also called as a mercurous chloride electrode. Okay, the construction part, it consists of a glass vessel having a bent side tube. The bottom of the glass vessel, a mercury is filled. Above the mercury, a paste of mercurous chloride is placed. The remaining portion is filled with a saturated decinormal or normal KCl solution. The bent tube is used to make a contact with the salt bridge. A simple platinum wire sealed by means of a glass tube is inserted in the middle of the mercury layer in order to provide an external electrical contact. It is represented like Hg bar Hg2Cl2 bar Cl minus. This electrode can act as anode as well as cathode, depending upon the nature of the other electrode in the cell. When the electrode acts as a anode, it undergo oxidation reaction. Here, the active component is a mercury. That mercury gives electron, forming mercurous ions. This mercurous ion takes chloride ion, forming mercurous chloride. So, the net anode reaction is mercury combined with chloride ion, forming mercurous chloride with the liberation of 2 moles of electron when the electrode acts as anode. When it acts as cathode, when you couple this electrode with another electrode, if that electrode acts as anode, that time Calomel electrode acts as cathode. That time the mercurous ion become an active ion and takes electron and forming mercury. This mercury formed by the dissociation of mercurous chloride, or in other words, mercurous chloride takes electron forming mercury and chloride ion. So we can write the net reversible reaction. Mercurous chloride takes electron forming mercury and chloride ions. So electrode potential of this electrode can be represented like this. E is equal to E naught minus 2.303 RT by NF log concentration of Cl minus to the power 2. Why I took this 2? Because in the reaction, reversible reaction, 2 moles of chloride is involved. So that's why I should take to the power 2. Okay. Then here number of electron transfer is n equal to 2. We can represent E is equal to E naught minus 2.303 RT by F log concentration of Cl minus. So the electrode potential that depends upon the chloride ion concentration. We may represent electrode potential that depends upon the chloride ion concentration. So at 298 Kelvin, when you use a saturated KCl solution, so you will get a potential of 0.2422 volt. When you use one normal KCl, that time you can get a potential of 0.281 volt. If you use 0.1 normal KCl, you can get 0.334 volt. Then what are the advantages of this electrode? A simple construction, cell potential is reproducible and stable over a long period, and it does not vary with the temperature. These are the main 3 basic things we observed in the in this electrode. Okay. I shall discuss about the application of Calomel electrode, that is determination of single electrode potential using Calomel electrode. The Calomel electrode is also called as a mercurous chloride electrode. So the Calomel electrode usually represent in terms of mercurous chloride, that is Hg2Cl2 bar Cl minus. In order to determine the single electrode potential of any other electrode, like zinc electrode, copper electrode, silver electrode, if you want to detect the electrode potential of any other electrode, that time that electrode, that is a metal, is like say zinc metal is dipped in a zinc rod, or a zinc metal is dipped in a zinc sulfate solution. Then that electrode should be coupled with the Calomel electrode. So the Calomel electrode potential is known, and it can act as an anode as well as a cathode depending upon the other electrode potential. Or we may get a positive EMF if we construct the cell in a right manner. That is the electrode whose potential is to be determined is taken as a left side, and the Calomel electrode right side. If you get a positive EMF, that indicates your construction is right. Then when a metal is dipped in a solution of zinc sulfate, then it is connected to a saturated Calomel electrode through voltmeter. So we may represent the cell like a zinc coupled with a zinc sulfate. Then it should be connected to a Calomel electrode like Cl minus Hg2Cl2 bar Hg through salt bridge. Internal connection is through salt bridge, and external connection is done by means of a wire through voltmeter. So pictorially, it can be represented this way, like a zinc metal. I'll take one zinc rod, dipped in a zinc sulfate solution, that is taken in a beaker, and it is dipped in a zinc sulfate solution. Then that should be kept left side. Okay, then only we'll get a positive EMF. Then I'll take a mercurous, that is a calomel electrode, and that calomel electrode I'll place right side of the cell. Okay, zinc electrode left side and calomel electrode right side, so that I can construct a cell. It's possible to get a positive EMF. Okay, I'll represent the calomel electrode. It contains a glass vessel. Bottom portion I place a mercury above, mercurous chloride. Then remaining portion usually filled with a normal or a decinormal or even saturated KCl. Usually while detecting the EMF of any cell using a calomel electrode, we use a saturated calomel electrode because it can withstand with the temperature and it does not vary during operation, okay, during the process. So then the calomel electrode I coupled by means of a wire through voltmeter. Okay, then so I'll just construct the cell like this. So it contains some bent tube as well as to introduce a KCl, saturated KCl, it has some side tube, okay, side bent tube, and both I immersed in a solution. That usually I'll take a zinc sulfate solution because zinc rod I used, so it should be dipped in a zinc sulfate solution. Okay, all things I represented this way, like mercurous chloride, that one, and it is mercury, and the remaining thing is this one, portion KCl. So we can represent this way. It's a systematic diagram. We can place that zinc calomel electrode outside the beaker or inside the beaker, no problem. It's just to make a connection because the zinc sulfate solution is used. It will not involved in the or interact with the calomel electrode. So that's why you keep that electrode outside, or you may keep it inside. Okay, this is about the construction of cell and the zinc. Now zinc act as anode and the calomel act as cathode. So a redox reaction takes place. A redox reaction takes place. Then EMF of the cell is determined. EMF of the cell is determined by potentiometric method. It is determined by means of a potentiometric method. Potentiometric method is nothing but we connect the two electrode to a potentiometer. Okay, then you know we write EMF of a cell can be represented as E cathode minus E anode, that is right side electrode minus left side electrode. The difference in the electrode potential of the two electrode give rise to cell potential. The right side electrode or a cathode is a standard calomel electrode minus a standard zinc electrode. So standard zinc electrode potential equal to calomel electrode potential, that is we can write it as E standard calomel electrode potential minus Ecell. So standard electrode potential is known, that is 0.2422 volt minus Ecell. So E naught Zn2 plus bar Zn, that is a zinc electrode potential or a single electrode potential of any electrode can be detected by using this formula. If the electrode act as anode, 0.2422 minus E cell. By knowing the EMF or by knowing the value of E cell, the E naught Zn2 plus bar Zn can be determined. Okay, this is how we use the calomel electrode while detecting the electrode potential, like a zinc electrode potential. Okay, that is the electrode which act as anode here. Same way we may use to detect the uh, electrode potential when the electrode act as a cathode. Okay, same way we can able to, here it act as anode, same way we can use it for to detect the electrode potential of any other electrode. Say the electrode act as a cathode, like that time we couple calomel electrode coupled with the another electrode, say copper electrode. That time the calomel electrode act as anode and the copper electrode act as cathode. So thereby we can able to construct a cell. Okay, let us discuss this one. How we detect the electrode potential when the given electrode act as a cathode. Okay, see, so we have to construct a cell. Again the same thing, the mercurous chloride electrode or the calomel electrode should be placed left side, and so we may write this way in order to determine the electrode potential of copper electrode. In order to determine the copper electrode potential, the copper metal should be dipped in a copper sulfate solution and it should be placed right side. Then it is simply connected to a calomel electrode, and the calomel electrode should be placed left side so that we can able to get a positive EMF. Like in order to determine the copper electrode potential, copper metal is dipped in a copper sulfate solution which is coupled with the calomel electrode. Uh, Externally, these are connected by means of a wire through voltmeter. Can be done by means of wire through voltmeter. Now I consider the representation of this cell. I already written. Anyway, again I will write. So we may represent this cell in this way. So anyway, you know the left electrode is a calomel electrode. So first you write a mercury, then mercurous chloride, then it in turn contact with the chloride ion. So salt bridge, then cupric ion is in contact with copper. So this way we can able to construct a cell. Then we should find out EMF by means of a potentiometer. So Ecell is equal to E cathode minus E anode. Now we know which one is a cathode. Cathode is a copper electrode. So we may write like E naught or E Cu2 plus bar Cu minus E standard calomel electrode. We know the electrode potential of this cell. We can able to calculate the electrode potential of this cell, and we know the standard electrode that is calomel electrode potential. So therefore we can write E copper electrode potential equal to E cell minus E standard calomel electrode. So in this way we can able to find the electrode potential of any other electrode, that is E copper electrode potential equal to E cell minus 0.2422 volt. I'll just substitute the standard calomel electrode potential. In this way we can able to detect the electrode potential of any other electrode. About Ionselective electrode, its construction and working. Before, what is Ionselective electrode? An ion-selective electrode is a one which selectively respond to a specific ion and develop a potential at the electrode in a mixture as a function of the concentration of that ion in a solution. So we can write it like this: ion-selective electrode is one which selectively respond to a specific ion and develop a potential at the electrode in a mixture as a function of the concentration that ion in a solution. Okay. Here, an electrode, say glass electrode, is an ion selective electrode. It is usually immersed in a solution. Okay, and this is a glass membrane which can able to respond a specific ion, say H plus ion, and it in the solution it may contains not only H, even Cl minus, Na plus, like different ions present. In that, this electrode is specific in action and develop a potential at the electrode in a mixture as a function of that particular ion, concentration of that ion. And that type of electrode, what we called it as a ion selective electrode. A good example for ion selective electrode is a glass electrode. Glass electrode is an ion selective electrode. Okay. See, in the electrode generally, the glass electrode or a ion selective electrode generally consists of a membrane. So that's why it is also called as a membrane electrode. And this membrane is capable of exchanging the specific ion with the solution with which it is in contact. Therefore, the electrode, it is also called as a membrane electrode. Okay. So we define a glass electrode or a particular ion selective electrode is a one which selectively respond to a specific ion and develop a potential at the electrode in a mixture as a function of that particular ion in a solution. Now I consider the construction and working of glass electrode. Okay, construction and working of glass electrode. So this is what the picture I shown. It is a glass electrode. Okay, this glass electrode consists of a thin walled glass bulb. And here in the glass electrode, we observe a thin walled glass. It consists of a glass bulb. It consists of a glass bulb, and this glass bulb is made up of a special type of glass with high electrical conductance. Usually, in the case of glass electrode, we use silicate glass may specially be selected for the purpose of to act as a glass membrane. Okay, and this glass bulb is filled with a particular normal solution, a standard solution, that is 1N HCl. Okay, the glass bulb is filled with a solution of N by 10 HCl, and simply this is an electrode, what we called it as a silver chloride electrode. Simply a silver chloride electrode is inserted at the middle of the bulb, act as an internal reference electrode. This is also called as internal reference electrode. Okay, and is connected for external electrical contact using platinum wire. Okay, connected by means of a platinum wire. The electrode is dipped in a solution containing H plus ion of different strength. Okay, it is dipped in a solution of H plus with a different strength. Here, it usually consists of, I already written, the thin walled glass bulb. This is a glass bulb made up of a special type of glass. Usually silicate glass are used for this purpose. And the glass bulb is filled with a decinormal HCl, which is act as an internal standard solution. Simply a silver chloride electrode inserted in the middle of the bulb act as an internal reference electrode and is connected to the platinum wire for external electrical contact. Okay. And the electrode usually dipped in a solution containing H plus ion. So this is dipped in a solution containing H plus ion of different concentration. It is other than 0.1 normal. Here, that's why this one is called as a analyte solution. Call it as a analyte solution. Presentation of electrode is here. It contains silver chloride electrode, and that is inside the bulb, and this in turn is contact with the point 1 or N by 10 HCl. In turn it contact with the glass bulb. So the representation of the electrode becomes Ag bar AgCl bar N by 10 HCl bar glass. So when you dip this electrode in a analyte solution, so that time the glass bulb is in turn contact with the analyte solution. So we may represent the cell, or we may represent the electrode when it is dipped in a solution, that is an analyte solution with the concentration of H plus ion C1, and inside the bulb, outside the bulb a gel layer is developed, and that gel layer develops a potential E1 volt, and outside the bulb it develops a potential E2. and it in turn contact with the internal solution N by 10 HCl with the concentration H plus ion equal to C2. In turn, it contacts with the internal reference electrode AgCl electrode. Here, the ion exchange reaction that takes place inside and outside the bulb due to difference in the concentration of the electrolyte. So, H plus ion of the external analyte solution is in contact with Na plus Gi, the membrane which contain Na plus ion, interact with the H plus ion of the analyte solution and releases Na plus, and the H plus ion is introduced or exchange. Na plus ion is exchanged with a H plus ion. So due to the difference in the H plus ion concentration inside and outside the glass bulb, a gel layer is developed across the glass bulb. That is, the migration of H plus ion inside and outside the bulb across the bulb that takes place. As a result, there is a development of a potential called it as boundary potential. This boundary potential is mainly due to the difference in the potential outside and inside the bulb. There exists outside the bulb the different concentration, whereas the inside the bulb the concentration is N by 10 HCl. As a result, a boundary potential is developed, and that boundary potential can be represented in the way that denoted by EB. The boundary potential is denoted by the term EB. The EB which is equal to E1 minus E2. That is the potential developed outside the bulb minus the potential developed inside the bulb. So EB equal to E1 minus E2. E1 minus E2, which is equal to, the Nernst equation, 2.303 RT by NF log C1 by C2, where the C1 and C2 are the concentrations. Here it is the development of some concentration cell, because due to difference in the concentration, same electrolyte of different concentration, we should represent in terms of Nernst equation for a concentration cell. So that's why we write 2.303 RT by NF log C1 by C2, where C1 is the concentration of H plus ion of the analyte solution. It is an analyte solution, and C2 is the concentration of H plus ion of the acid solution, which is inside the gas bulb. Okay, and it is always constant. Usually we'll take 0.1 N HCl. That is throughout in the while manufacturing. So we'll use a 0.1 N HCl. So C2 is a constant, and number of electron transfer during the reaction is N, that is equal to 1. Always there is a H plus ion, so N is equal to number of electron transfer is equal to 1. So C2 is constant, N is equal to 1. Substitute these things in the first previous equation. So we'll get equation like EB which is equal to constant term. That constant term is nothing but minus 2.303 RT by F log C1, or we may write like EB is equal to constant plus 2.303 RT by NF log C1. So we represent like 2.303 RT by NF log C1, where we can write the constant what we represent. It is equal to, we may put a term L, which is equal to minus 2.303 RT by NF log C2. And the N is equal to 1, or we may represent at 298 Kelvin. This equation can be represented this way. EB is equal to L plus L plus 0.0592 pH, because N is equal to 1. Okay, and instead of writing pH, we may write like log C1. I'll represent like that only. EB is equal to L plus 0.0592 log C1. And you know that the log C1 is equal to minus pH, or you know the equation pH is equal to minus log concentration of H plus. In this case, pH is equal to minus log C1, or we may represent EB is equal to L minus 0.0592 pH. Here, EB, from the equation, we predict that EB depends upon or depends only upon the concentration of H plus ion. Okay. So now we can represent the combined glass electrode. When we check the want to check the concentration of H plus ion, we should use a combined electrode. We represent this way. The combined glass electrode is immersed in an acidic solution. Then the potential of the glass electrode, we represent Eg, is given by, okay, the combined glass electrode, usually it is immersed in an acidic solution. Then the potential of the glass electrode, Eg, is given by, it consists of three terms. We may represent like Eg equal to EB plus E reference plus E estimate. Eg equal to EB, that is a boundary potential, plus E reference plus E asymmetry. Okay, so we can write where EB, E reference and E asymmetry. What is that EB? EB is nothing but boundary potential. So EB are boundary potential, reference electrode potential, and a small asymmetry potential. You know, EB and E reference is well known. And what is the third term, E asymmetry? So we can predict E asymmetry. It is particularly observed in the case of a glass electrode, not in all the electrodes. Particularly in case of glass electrode, we observe a small asymmetry potential. Okay, because of the formation of a gel layer, a small asymmetry potential is developed. So theoretically, we consider the EB is equal to 0. You know the equations. So EB equal to E1 minus E2, or we can represent 2.303 RT by NF log C1 by C2. Log C1 C1 by C2, if it is equal, then EB should be 0. But however, a small, when C1 equal to C2, however, a small additional asymmetric potential contribution exists. Okay, a small asymmetric, that is E1 C1, if you take a same concentration inside and outside the glass bulb, but there exists a small potential. And that potential, what we called it as a asymmetric potential. Okay, a contribution exists even when C1 equal to C2. Thus we can write the glass electrode potential is the sum of three terms, and you know EB value. So I may represent EG equal to L minus 0.0592 or 1 pH plus E silver electrode potential. Reference electrode, here we use a silver electrode, so a plus E Ag bar by bar AgCl electrode plus E asymmetry. And we may represent the glass electrode potential like Eg equal to E naught G minus 0.0591 pH. And what is E naught G? Where E naught G is the sum of the constant terms L plus E Ag bar AgCl plus E asymmetry. Okay, in this way we can able to predict the electrode potential of a glass electrode. Okay, so the glass electrode potential is Eg equal to E naught G minus 0.0591 pH. So what is the advantages of this electrode? The main advantage of this electrode is this electrode can be used in an oxidizing or the reducing environment. It can be used even in the presence of an oxidizing agent or a reducing agent. Okay. Then the other thing is the electrode does not get poisoned. The electrode does not get poisoned. Only the silver chloride electrode is inserted in a 0.1 NHCl, whereas the platinum wire is present in the external circuit, so electrode does not get poisoned. And the third advantage is by using special glass electrodes, pH 1 to 14 can be measured. By using a special glass electrode, the pH 1 to 14 can be measured. Okay, so these are the three important advantages of glass electrode. Okay, then I'll consider the disadvantages of this electrode. There are few disadvantages of this electrode. The main the disadvantage I already discussed. It can able to find a pH up to 14, but to find the pH around 12, we have to use a special glass electrode. Okay, a special glass electrode can measure up to pH 12. Okay, it is possible up to pH 12. Above 12 pH, usually cations of the solution affect the glass interface and render the electrode useless. Usually above 12 pH, cations which present in the solution, they adhere on the electrode surface. As a result, the electrode becomes useless. Okay, above 12 pH, cations of the solution affect the glass interface and render the electrode useless. Then the second disadvantage what we observed is if you use a very low pH value, that time the anion come into picture. That is the acidic solution. It has highly acidic solution of pH less than 1. Okay, the acidic solution of pH less than 1, the salt effect due to the anions are observed. The salt effects due to anions are observed. Okay, then the third disadvantage what we observed in this electrode is because of high resistance of glass. Okay, here we use a high thin glass bulb with high electrical conductance but high resistance of glass. It is necessary to use a special electronic potentiometer. Okay, the ordinary potentiometer is not sufficient if you want to measure a very low or a very high pH. Then a special electronic potentiometer is required. Because of high resistance of glass, it is necessary to use special electronic potentiometer. Okay, so these are the few disadvantages of this electrode. And then application of this electrode, the main application of this electrode is this electrode can be used to measure the pH of a solution. The electrode is mainly used to measure the pH of the solution. pH of any given solution can be measured. The topic: determination of pH using glass electrode. So here we can able to detect the concentration of H plus ion in a solution. You know, the glass electrode is a pH sensitive electrode. It detect the concentration of H plus ion of the analyte solution. In order to determine the pH of a glass electrode or pH of a solution using glass electrode, we have to construct a cell. So in a cell there are two electrodes. In that the one electrode is a glass electrode and second electrode what we used is a Calomel electrode. By convention, the glass electrode, I'll take it as a cathode and the Calomel electrode, I place it as an anode. So the glass electrode dipped in an analyte solution whose pH is to be determined. Then it is coupled with a reference electrode such as Calomel electrode through voltmeter. So the constructions can be shown in the diagram. Can represent this cell like a representation of cell. So you know the right side electrode what we used is a glass electrode and the left side electrode is a Calomel electrode. While representing the cell, the first you have to write a left side electrode, that is Hg bar Hg2 Cl2 bar Cl minus. Double bar that indicates the salt bridge. Then that electrode is dipped in a solution whose pH is to be determined, which in turn contact with a glass bulb. In the glass bulb, we observe 0.1 m HCl, internal standard solution. In turn, it is in contact with the silver chloride electrode. Okay, AgCl electrode. Then we can write, or we can find out the EMF of this cell by using a potentiometer, and we can represent E cell equal to E cathode minus E anode. The cathode electrode is a glass electrode standard, or the glass electrode, minus the E anode, that is a standard Calomel electrode, SCE. Then, so by convention, why I took the Calomel electrode, it is by convention. The Calomel electrode is taken as anode by convention. Next, I can write the E glass electrode potential like E naught G minus 0.0591 pH. I know E cell, that is equal to E naught G, that is standard electrode potential of glass electrode, minus 0.0592 pH minus standard Calomel electrode. Okay. Now, in the equation, I can find the pH. So I can take it in take it to one side. That is minus 0.0592 pH. That is equal to E cell minus E naught G minus standard Calomel electrode. My intention is to detect the pH of a solution. So that's why I can write pH equal to E naught G minus E cell minus standard Calomel electrode divided by 0.0592. Never stop learning, because life never stops teaching. So watch my next video, which is on energy storage system, and that will study a classification of batteries and explanation of construction and working of few batteries.